uh, given to correct that to Sarit sir.
Sarit sir. Oh, it's good. It's. I think my PPT is sharing on.
Yes, sir. It is.
It's full screen,
yeah,
right?
It's full screen right now.
Okay.
Good, sir. Perfect. Thank you.
I'll stop sharing now. So your area of research, sir, Dr. Rock, sir?
Computational heat transfer.
Oh, computation. Very nice, very nice. So you're focusing on heat transfer enhancement or something?
Micro heat pipes was actually my
work. Micro heat pipes. Oh, very nice.
Under Dr. C.B. Chopin.
Oh, okay. I know. Chopin, I heard about. Satyan, Sarit Satyan and Chopin, they are working in NIT Calicut. That center they have started, right? Center.
Nano Center for Nanotechnology.
Nanotechnology. Yes. I heard about that. So what was the conference? All 3 days it was. I mean, 2 days completed. Today is the last day, right?
Today is the last day, sir.
Okay.
It's going on. It's going on well.
Oh, very nice, very nice, very nice. So we are organizing an IHM. Okay. It's going to record, it seems.
Yeah. Yes, sir.
So we are organizing an IHMTC conference December, IIT Madras.
Okay. ISHMT, Indian Society for Heat and Mass Transfer.
Yes, sir.
Okay. There is a Trivandrum chapter. Actually, I am a member of Trivandrum chapter.
Oh, okay. Okay.
Dr. Pisharidi from ISRO is actually the secretary of the Trivandrum chapter.
Oh, okay.
The Trivandrum chapter is active. They are organizing a series of webinars now.
Mm-hmm.
Sir Arul sir, shall we start, sir?
Yes, ma'am, we'll start.
Sir Rak sir,
okay.
Shall we start?
Yes, madam. Yes, madam.
So I'm sharing the screen once again.
Sir, I'll hand over for the introduction. Sanju sir, please.
Yes, ma'am. Yes, ma'am. Yeah. We are together again on the third day of International Conference on Computing in Mechanical Engineering 2021. Ladies and gentlemen, very good morning to you all. Myself, Sanju AC, Assistant Professor in the Department of Mechanical Engineering, ICCME School of Engineering and Technology. Now we have the start of the keynote sessions. We have a very distinguished guest here with us. I would like to invite Dr. Rag RL, convener ICCME 2021, professor and head of the Department of Mechanical Engineering, ICCME School of Engineering and Technology, to welcome the keynote speaker. Over to you, sir.
Thank you, Sanjay sir. Am I audible?
Yes, sir, you are.
Our respected keynote speaker, Professor Dr. K. Arul Prakash sir, other dignitaries and dear participants. A very good morning to all of you. We have reached the last day of ICCME 21. On the very first day, we have Professor Dr. Gerardo Carvajal and Dr. C.B. Chopin for the keynote sessions. The plenary session was led by Professor Dr. Dean Ushnish. Yesterday, we had Dr. B.V. Reddy and Dr. Alam Mohammad Mahbub as our keynote speakers. It gives me great pleasure and privilege to introduce and welcome Dr. K. Arul Prakash to this keynote session. Professor Dr. K. Arul Prakash is currently a professor in the Department of Applied Mechanics, IIT Madras. His broad areas of research are fluid mechanics, turbulent flows, heat transfer, and numerical methods. Specific topics of research currently being pursued are computational fluid dynamics and heat transfer, cooling technologies, thermal hydraulics, aerodynamics, optimization, and parallel computing. He has more than 20 publications in international journals of higher repute. He is also the editor of a book on computational heat transfer, published by Progress in Computational Heat and Mass Transfer, Paris. He has received funding for projects from sponsoring agencies including Aeronautical Development and Research Board and Department of Science and Technology, Government of India. On behalf of the organizers and participants of ICCME 21, from the bottom of my heart, I extend a warm welcome to you, sir. I also welcome all the dignitaries and participants to this keynote session. Thank you.
So, my voice is audible, right?
Yes, sir. Yes, sir. Yes, sir.
And it's in full screen. My screen is in full screen.
Yes, yes,
Okay.
it's clear.
So, first of all, I thank Dr. Rag Ariel, head of the department, for kindly introducing about me. And I also thank the organizing committee of ICCME 2021 and the management of SSET College for kindly inviting me to deliver this keynote lecture. It is my honor to deliver the keynote lecture in this ICCME 21. So I extend my thanks to all the organizing committee and personally to Vidya Chandran, Dr. Vidya Chandran, so who is in touch with me all the time for inviting from the beginning of the conference. Thank you everyone. And the topic of my talk is turbulent fluid flow and heat transfer characteristics over textured superhydrophobic surface. So myself, Arul Prakash, a professor from the Department of Applied Mechanics, IIT Madras. So the outline of my talk is, the outline of my talk goes like this. I will give a brief overview of superhydrophobic surface, an introduction about superhydrophobic surface. So many of them knows what is superhydrophobic surface. So I will give how we can utilize this superhydrophobic surface for various applications. So what is the motivation for utilizing this superhydrophobic surface for various applications? Then comes the objectives. And before simulating, I just want to, before doing the simulations of superhydrophobic surface, what are the different turbulent simulation techniques available? I'll just give an overview, and how we are modeling this simulation of superhydrophobic surfaces using one of the turbulence simulation technique that is called as direct numerical simulation. So mainly we are focusing on the governing equations, what is the numerical methodology and validations. Finally, we will discuss two types of, totally three types of superhydrophobic surface and two types of superhydrophobic surface which is available in the literature, scientific community, that is called as straight ridges and the square posts. And finally, we have developed a novel superhydrophobic surface in our laboratory using our past experience. And that I'm going to present how this is advantage over the other two superhydrophobic surface present in the literature, followed by the conclusions. Okay. So basically, super hydrophobic surface. What is meant by super hydrophobic surfaces? This is a micro textured substrate with surface treatment. For example, it is available in natural many leaves, it's like a lotus leaves, and also the taro leaves, and also in some wings of the certain insects. Okay. So what is the advantage is when you pour the water on this super hydrophobic surface, the water will not stick inside, means over the surface. So it is something like a waterproof. Okay. So we will take this as an advantage because over this layer of the leaf or means wings, there is a small layer will be there which will resist the mixing of water with the leaves. Okay, so with the help of super hydrophobic surface, about 99% of dirt on the surface is washed away. Okay, so therefore we will keep that surface almost all the time to be clean. And what is the advantage is we can reduce the drag. If you coat the super hydrophobic surface, if it is exposed to some fluid flow, then we can see that when compared to the normal solid surface, this super hydrophobic coated surface will have about 70% of drag reduction. That is, we will control the turbulent boundary layer in some controlled experiments, which we have theoretically proved, and practically maybe less, means more than 50% drag reduction is feasible by coating this super hydrophobic surfaces. So what are the different kinds of applications? So we can see. So one is the inkjet printers. We can use this super hydrophobic surface in the inkjet printers where the ink, etc., will not stick to the surface of the contact, and also transport contacts also. In order to reduce the friction factor, we will, if it is in a pipe, we will coat the super hydrophobic surface inside the pipe. Thereby, we can get enormous advantage in terms of pumping power, and also the marine applications. Basically, you will coat the super hydrophobic surfaces on the surface of some ship or a submarine and some other means AUV autonomous vehicle, etc. So thereby you will reduce the drag so that you can improve the pumping power, and also at the same time we can also this coating will prevent some sort of corrosion and some stresses, mechanical stresses, which is directly impact on this surface of the marine structures, etc., can be possible with the help of super hydrophobic surface. And anti-icing. Suppose if you don't want to some surface to be on some cold conditions, if you cover with the super hydrophobic surfaces, this anti-icing, means icing cannot be formed with the help of super hydrophobic surfaces. And self cleaning automotive glasses. For example, the glasses are very sensitive structures. When you coat with the super hydrophobic surfaces, the glasses will get up. It is prevented from some dirts. And also dew harvesting, basically in the case of some earth, if you go for some desert conditions, so if it's difficulty to get the water in some places, so what you will do is you will have a small surface and you will coat with that surface with the super hydrophobic surfaces. So you will place it in the atmosphere. So thereby, when the wind is passed, the dew will be collected on the super hydrophobic surfaces, and then you will collect the dew. Once when dew is collected, once in the next next day, subsequent day. So thereby you will harvest the water from this super hydrophobic surfaces, and also it will be useful in the solar thermal energy collectors with the low maintenance solar thermal energy collectors, etc. Okay. So what is meant by super hydrophobic surfaces? So basically, you are having a bubble or water drop. The angle between the free surface of the drop with the solid subject. This is a solid subject. So that angle is called as contact angle, theta. Okay. So the free surface and the solid surface, a solid object, it's called as the contact angle. When the value of theta is less than 90 degrees, then we are calling this non-hydrophobic or hydrophilic surfaces. So for example, glass. And when theta is greater than 90 degrees, then we are calling it as hydrophobic surface. And when theta exceeds 150 degrees, then we are calling it as super hydrophobic surface. This is the difference between three surfaces. When theta less than 90, hydrophilic. and greater than 90, it is hydrophobic. And if it is exceeds 150 degree, we are calling it as super hydrophobic surface. Okay. So what is the textures? So these are the some of the textures which is structurally structured super hydrophobic surfaces. This is specially engineered microscale structures with precise patterns of micro or nanometer size ridges or pores. Basically, you can see that these are some small structures. This is magnified up to something like 100x, and this is magnified. This figure is magnified up to 1000x. You can see that the small structures, something like a small lines with some height, it's almost very, very small. We cannot observe in the naked eye. If you see in the microscope, you can see this one. So these are the small ridges, which is we are structured using lithography or some other techniques. Then we will put it on the surface. That is called as so structured super, specifically engineered microscale structures. So the structures which are showing here is called as ridges. So you can see that there is a small line. So continuous line. This is a no slip line. This is means flowing across the surface, and this is a post. I'll show a better picture in the next slide. So how the difference between the ridges and the posts will be there. So what is the main thing is it allows the slip velocity in between. This is you can see that there is a the wall, the ridge wall, and in between this ridge wall there is a air gap is there. So that creates some large slip velocity in between this air pockets. So similarly, in the case of post also, you can see that these are the air packets. So there are two types of super hydrophobic surfaces states are available. One is called as Wenzel state. Other one is Casey-Baxter state. So what is meant by Wenzel state is means Casey state means this is a drop, and this is the super hydrophobic surface. And if the drop is not penetrating to the surface, then it is called as Casey state. That is small scale surface roughness. This is the small scale surface roughness prevents the water. So mainly now we are focusing the applications in with respect to water. So therefore I'm showing the examples with reference to the water. So prevents the water from moving into the space, resulting in air-water interface. This is called as Casey state, and this is a truly super hydrophobic and significant drag reductions in both significant drag reduction in both laminar and turbulent flows will take place in the Casey state. The next one is called as Wenzel state, where the drop penetrates into the textured surface, and that is water penetrates into the corrugation of surface. So what Wenzel state happens is sometimes it will end up with detrimental effects, like either a drastic drag reduction. Sometimes there is no drag reduction will take place. That's the difference between Casey state and Wenzel state. Always the Casey state will be advantageous. Therefore, we are doing the simulations with reference to the Casey state. Sometimes the Casey state also, the state may be switched from Casey to Wenzel state after long exposure, as the interface will fail due to some scenarios. So what is the motivation for studying the super hydrophobic surface? We saw that there are many applications. Basically, if you see that this micro surface, this structure surface is very, very small surface, which is restricted to, if you see the any wall, you are having a different surface. One is called as laminar surface, laminar sublayer, followed by buffer layer, and followed by outer region. So this mainly the super hydrophobic surface will perturb or will create some disturbance only in the laminar sublayer. Okay, so our focus is mainly on the laminar sublayer. A small alteration in this laminar sublayer will create the complete change in the entire turbulent boundary layer. So that is the observation by Fugata 2006. So if you make a small change in the surface of the some solid surface, this will create the complete change in the turbulent boundary layer, and there will be secondary flow pattern will also happen. So because of the presence of no slip and free slip, no slip and free slip, there is a change in the velocity gradient or pressure gradient, and which will create the recirculation regions inside the near to the wall, and this is called secondary flow pattern. So this was observed in Jelly et al. In 2014 by also Turk et al. And so the study is further extended because of this recirculation region, which is caused due to the superhydrophobic surface, whether there is an enhancement in the heat transfer takes place. So that's what we want to investigate. So that heat transfer studies were mainly focused in the laminar regimes on the micro channels, etc. These mechanisms are not focused. Mainly, they are not dealing with some what is the change in the laminar sublayer of the microchannel or any texture surface, etc. Also, there is no studies, even though it is not done in the laminar, it is whether we can done in the turbulent, so that is also not performed, the studies. Therefore, there is a high chance, that means high motivation that this can be extended, these studies can be extended to the turbulent region by systematically investigating the impact of the structural spacing, the texture, whatever the engineered structures which were stored, by changing the various parameters like distance, etc., we see how whether there will be any enhancement in the heat transfer. Okay. So the studies indicated a reduced heat transfer in turbulent region. So obviously we know that when you are tampering or when we are covering a surface with any textures, obviously there is the surface area will become reduced, and there is a reduction in the heat transfer. So that reduction on the heat transfer also not yet studied in either in the laminar region or the tubular region, or with reference to any specific texture characteristics also. So that is all not studied in detail till date. So a need for accurate understanding into the root and mechanisms of heat flow, and therefore mainly the flow characteristics, and with in turn the heat transfer or mass transfer, any other passive scalar transfer is very much essential to use the superhydrophobic surfaces in the industrial applications or scientific applications. So that forms the motivation for our study to analyze the superhydrophobic surface. We have taken two surfaces from the literature, and one which we are modified, which can be used, which is having the enhanced performance when compared to the structures present in the open literature. So with that motivations, we have framed the objectives, that is to investigate the effect of future spacing on drag reduction and heat transfer over superhydrophobic surface using direct numerical simulations. Okay. So I will also discuss about different types of turbulent simulation techniques. So why we selected direct numerical simulation techniques? Because other models will never capture extensively the physics of this the superhydrophobic surface. Therefore, we are using the DNS section to critically assess and compare the fluid flow and thermal performance of streamwise aligned ridges and posts. This is a typical surface. You assume that this is a channel, and in this we are aligning. This is the ridges, the black colored patches which you are seeing are the ridges. So we are along the streamwise directions. We are aligning the ridges, and this is called as a straight means channel with straight ridge texture superhydrophobic surface. And the second case is the square posts. So we are not, in this case, straight ridge, we are introducing the no slip and the free slip only in the spanwise direction, whereas in this case we are introducing the no slip and the free slip in the streamwise direction also. So the second one is called as square posts. Okay, the first one straight ridges and square posts, which is aligned along the streamwise directions. So first we are going to assess and compare the fluid flow and thermal performance characteristics of streamwise aligned ridges and the posts. And finally, with this knowledge, we have designed a new novel structure that is called sinusoidal ridges. And we want to understand the effect of spatial modulation of superhydrophobic surface texture on fluid flow and heat transfer in the sinusoidal structure. So this is what designed. So this is a structure in the channel. Say something like this is not like a snake along the surface. So where both the streamwise and spanwise slip and no slip conditions can be integrated and can be given in this surface. Okay, the sinusoidal. So if you follow this means a sine curve, there is a there is a no slip and free slip characteristics in the span-wise direction, that is in the Z direction also, the span-wise direction, and also in the stream-wise direction. If you move along the sine curve, suddenly you will encounter the no slip from no slip region to the free slip region, and both in the stream-wise, and from the free slip region to the no slip region, all along the stream-wise direction, and also along the span-wise directions. So these are the main three objectives. First, we understand about what is feature spacing on drag reduction and the heat transfer over the some specific superhydraulic surface, mainly on the stream-wise aligned bridges and the posts. And finally, we are going to see what is the effect on the sinusoidal ridges on the fluid flow heat transfer when compared, and we also comparing with stream-wise aligned ridges and the posts, how it is advantageous for the practical applications, mainly in terms of drag reduction and also in terms of enhancing the heat transfer. So with this understanding, so we adapted a technique called as direct numerical simulations. Why we are taken this direct numerical simulation techniques? So to discuss about this, I will just give a small introduction about the simulating a turbulent flow. Just an overview of the simulating a turbulent flow. The turbulent transport is mainly due to the vertical motions, that is called as eddies. Suppose if you are having a high speed fluid and the low speed fluid, if you see that when two fluids are interacting, then there is some instability, that is a free shear instability, that is called as Helmholtz instability will take place, and you will get a structures like this. Suppose if I want to capture these structures, what are the techniques available? This is a high speed flow and this is a low speed flow. You can see some similar kind of structures in our clouds. Sometimes if you see the sky, some kind of structures are also which is visible. So this is mainly due to the movement of high speed. There is interaction between the high speed fluid and the low speed fluid. So the turbulent simulations can be performed using three approaches in order to simulate this one. One is called as direct numerical simulations, which you are going to use in the study. And the second one is called as Reynolds average Navier-Stokes equation, that is called as RANS. And the third one is called as large eddy simulations, okay, that is called as LES. So what is DNS? DNS is nothing but it will give the full description of all the eddies. So suppose if this is a eddies formed, the complete description of all the eddies present in the structure, means in the flow domain, can be captured with the help of DNS, the direct numerical simulation. Obviously, the penalty is we want to give we want to invest a lot of computationals. Okay, the computational cost is enormous in the case of direct numerical simulation. And the second one is, I can see the mesh. I can see that for capturing some gradients in this particular region, you want to use a mesh, means the fine mesh, something similar kind of mesh which is shown in this figure. And if you want to use the same simulations, if you want to use RANS, it is nothing but only the statistical distribution of all the eddies. So we can you can use a mesh which is very coarse when compared with the DNS. You can see the difference between the mesh of RANS and DNS. Whereas if you want to further have an accuracy when compared with DNS, but when accuracy when compared with the RANS, but less accurate when compared with the DNS, the intermediate simulation is called as large eddy simulations. So this is only the partial description of the eddies. So you can see the typical mesh size is shown here. So there are three types of simulation techniques of the turbulent flows. One is direct numerical simulation, other one is called RANS, and the third one is large eddy simulations. And you can see that in the direct numerical simulation only we will capture the complete structures of the turbulent flows. So therefore we are looking at the very micro level. So therefore both LES and the RANS is unable to capture all the structures near to the sublayer level. Therefore we are using the direct numerical simulations for our simulation. So why we are using a direct numerical simulation is it's a multi-point and non-invasive information. And the frequency also, we also get the information about the frequency and the wave number. And there is no modeling at all, unlike in RANS and LES subgrid scale modeling. We are not having any modeling in the case of DNS. Therefore, we will have an increased accuracy. We can see that if you run continuously if you repeat the simulations, you will see that more faithful reproduction of the flow physics is achieved with the help of direct numerical simulations. Okay. So therefore, we are proceed further to model the super hydrophobic surface using direct numerical simulations. So these are the governing equations. This is a continuity equation. We are using we are assuming that this is because it's a water, we are assuming it is an incompressible fluid. So therefore, the governing equations are the Navier-Stokes equations. This is given by this unsteady term, convection term, the pressure term, that is the source term, and the diffusion term, and this is the continuity equation. And this is the energy equations, the convection term, and this is the diffusion term. And we are non-dimensionalizing this one. So therefore, we are getting a term called as a Reynolds number based on tau, that is called as a friction Reynolds number. Okay, so the velocity we are using is nothing but not the actual velocity, but it's the friction velocity, and the Prandtl number is nothing but it's a ratio of kinematic viscosity to the thermal diffusivity. Okay. And here UI we are represented in terms of a tensor. So U, V, and W are the velocities along the X, Y, and Z directions. So we are considering the Cartesian coordinates for solving this problem. And some details about the turbulent quantity U tau is given by square root of tau W by rho, where tau W is the shear stress and rho is the density. So in the inner layer, the turbulent is very near to the wall. The inner layer means near the wall. The turbulence is universal, so independent of the rest of the flow. It is behave more like a laminar sublayer. Okay, so it's because most of the turbulent disturbance which is created is caused is it will dissipate in the form of a heat because of the viscosity. Mainly, so therefore it will depends mainly on the viscosity and the viscous shear stress near to the wall. And the friction velocity is given by this quantity. This is given by tau W is nothing but square root means mu into, that is mu into dou U by dou Y by using the Newton's law of viscosity, and mu by rho, that is a nu, and Q bar is the mean velocity, and this is the velocity scale which is given by V by U tau. The outer layer, the influence of the viscosity near to the wall becomes negligible, so that we can see the large structures near and along the outer layer, whereas near the wall it is mainly the laminar sublayer. Okay, so the size of the large eddies scales, we are defining different parameters. So we have taken this the height of this super hydrophobic surface as 2 delta. So we can take the half width of the channel as our the characteristic length. We are taking only the delta as our characteristic length, both in the case of straight ridge pose and also the sinusoidal ridge. So based on the delta, we are defining all the quantities. So therefore, the U plus is given by U plus U by U tau, and the length can be given along the streamwise direction. It is given as xi star, and time t star, and the pressure is P plus, and the temperature T, and according to the scaling is given in the right hand side. So this is the basically two structures we are going to see. One has straight ridge and the square pose. We fix the Reynolds number because based on the literature, most of the studies happened at the Reynolds tau, the friction Reynolds number at 180. Therefore, we fix the friction Reynolds number as 180, and there is a flow is happening due to the pressure gradient along the streamwise direction. That is, we are giving a constant pressure gradient in the streamwise direction is directly proportional to the friction velocity, that is rho U tau squared by delta, that we are giving as an inlet incoming velocity, the pressure gradient, so that there is a velocity along the streamwise direction. If you closely look into the surface, because this is the width of the free slip surface, that is means the ridge is given by the distance between the two ridges is given by L, and half of this thing is the free slip region, and half of this thing is the ridge length, which is given by W. So L always we are taking as W is equal to L. So with this we are proceeding, but in practical situations this can also be varied. So this is our simple assumption we have taken for solving the problem very easily. And the length of the channel is given by, because it's a periodic along the streamwise direction and also the spanwise direction. So we are defining in terms of pi. So in the length can be given as 2 pi into delta, and that is the length of the streamwise direction, and the length of the spanwise direction is also pi delta, and the height is given by 2 delta. So these are the some of the geometry specifications of this domain, and you can see that this is the free slip region and this is the no slip region along the spanwise direction in the case of ridge, whereas in the case of suppose it is there both in the streamwise and also the spanwise directions. And these are the boundary conditions. So along the ridges, So the black patch, the velocity U, V, and W is equal to 0. And along the interfaces and the free slips and no penetration boundary, so mainly along the no slip region, okay, the white region. So we are having the free slip boundary that is given by dou U by dou Y is equal to 0, and V is equal to 0, and dou W by dou Y is equal to 0. That is a general free slip boundary conditions given to any channel flow. And we are heating the bottom plate in order to study the temperature variations. We are heating the bottom plate, only the no slip region with some temperature T is equal to 1, and the top surface is kept at the ambient condition and is 0. So these are the non-dimensional. Therefore, we are representing as 1 and 0 here. And liquid gas interface. So along the liquid gas interface, we are taking it as adiabatic. There is no heat transfer between the fluid and the solid surface. So we are always assuming this is a Cartesian state where the drop is not penetrating to the solid surface. Okay. So this is the computational scheme. We have used the finite difference scheme using a fractional step method using based on Corinne. And this is a semi-implicit time advancement. We are using the viscous terms using Crank-Nicholson scheme. And second order explicit Adam-Bosworth scheme is also used for convection scheme. And fourth order central difference energy conversion scheme is used for all the spatial terms. And we are using a staggered grid. So this is the way how we are storing the variables. So the pressure is stored at the cell center, on the velocity is stored at the cell faces. Therefore, we are using the staggered grid with pressure located at the cell center and the velocities at the cell faces we are using. And the pressure Poisson is solved using generalized mean residual method. And we are also parallelized using MPI, message passage interface method. And this is the typical computational grid. So this is the ridge we are showing here. And you can see the magnified image of the ridge. I can see that how much fine the mesh is, so that we can capture the complete structures using our direct numerical simulations. So basically, we will call this unit in terms of y plus. That is nothing but y u tau by mu. That value of y tau means u plus is not, y plus is almost equal to 0.1. And this is the typical the wall normal direction. And this is your wall. And the magnified view of the wall is going here, so that you can see that 0.001, like that we are using the along the z direction is this is the spanwise direction. Along the y direction, you can see that almost the small region covered with so many grid points with the value of y is equal to 0.1. Therefore, y plus is still smaller value of the order of 0.1. So to do the validation, this is a simple channel we have taken. So this is the flow is coming here, and we have taken a periodic along the streamwise direction and also the spanwise direction. We have taken the periodic direction, and we are comparing the velocity. And only in the bottom, we are giving a super hydrophilic surface. Okay, the general surface we are keeping, and to see what is happening to the super hydrophilic surface. Whereas in the top, we are having the no slip velocity. So when you see that, when you are having a no slip velocity, you can see that the velocity is 0 near the wall. When you are having a super hydrophilic surface, we can see that there is a small slip velocity is present. So this is the length of the super hydrophilic surface, the height of the super hydrophilic surface, which is covered only the laminar sublayer. So when you plot the velocity, so basically it is a parabolic velocity. In the right hand side, the top region, since it is a no slip region, so this is the no slip region top. We are plotting the velocity along the streamwise direction, along with the spanwise distance. So that is along the velocity along the spanwise distance. So we can see that the upper wall at y is equal to 2, you can see that the velocity value is velocity is 2. Whereas in the left wall, because of this velocity, because of the presence of the super hydrophilic surface, there is a velocity which is given by this phi, and this we compared with analytical solutions, which is that is Martel et al. Solutions, and it is found to be means nicely matching with the results, and therefore we can tell that our code is validated. Okay. And also we have compared different stresses, Reynolds stresses, that is product of u dash u dash b dash and b dash w dash, and also we have compared with the standard results of Martel et al., and we found that the results are found to be extremely agreeing. Means our scheme is good in agreeing in terms of agreement with the literature data. So therefore, then we have proceed further in simulating the super hydrophilic surface using our in-house code. So this is the how the different cases we have considered. So as I told earlier, we are having first we are considering the ridges and the posts. And ridges means this is traveling perpendicular to this screen all through the length of the channel. And post means we are having some distance. We have a distance of L. And so first square post, the first one is no slip region. So the complete wall means the surface of this is a no slip. There is no some grooves like this. So it is a complete flat wall. This is a no slip boundary. And the second case is a P18. The P18 is something like a square post. P represents the post, R represents the ridges. So this is the notation. So we have changed the value of L to from 18 to 70. The length of the superhydropic surface length, the texture superhydropic surface, we have changed from 18 to 70. So this we are doing in terms of wall units, not the actual units. And exactly W is equal to L by 2. So we have taken off of that one as the no slip region, ridge length. So therefore, you will the number of ridges, etc., will vary based on the length of your superhydropic surface. Same thing we are doing with the help of ridges also. So accordingly, the delta x plus and delta y plus, that is the distance between the first grid point of with reference to the along the streamwise direction and the normal direction, and also the spanwise directions will change. And we are usually basically, but the no slip case, we are using nx, ny, and nz as 512 grid points, and that is also we did the mesh independent study, and we have done compared with the literature also results. Therefore, 512 is sufficient to simulate such kind of cases. So, but when you are changing the number, means the length with L plus is equal to 18, etc. So the number of grid points along the spanwise directions will change. So therefore, if you see that in the case of P18, the number of grid points is 1024. Means whereas in the case of P70, you can see that we are using the 512. Okay, only in the spanwise direction, number of grid points will change. Whereas in the case of wall normal, always 512 remains a constant. But in the case of P38, then the number of distance also will vary. So therefore, decreases. So therefore, in the case only in the case of posts only, because the posts are nothing but we are having a different no slip and free slip in the streamwise direction also. So these are all about the details of the grids, and we found that by adding this superhydropic surface with the posts, we are getting about 37.2%. I'll explain how we are getting why we are getting the drag reduction percentage in the next slide. And with reference to the ridges, we are getting a reduction of about 28.8% reduction when compared with the no slip wall. So by adding a surface like this, a texture like this, we are getting a drastic reduction in the case of drag. So this is the velocity profile plotted with reference to U plus versus Y plus. This is the standard way of representing the velocity profile for turbulent flows. So we can see that we subtracted U slip velocity, which is caused due to the presence of superhydropic surface. So therefore, this is the no slip region. The dark blue color line, solid line, is the no slip wall, and this is the analytical expression. So till the laminar sublayer, it follows the linear profile. So because this is the log-law profile, therefore it is a linear profile. U plus is equal to Y plus is the linear profile, and from this it will follow the log-law. U plus is equal to 1 by 0.41 ln Y plus 5.5. This constant is the depends upon the roughness. So when you are adding the superhydropic surface like P18, R18, P56, R56, etc., you can see that there is no change in we are altering near to the laminar sublayer, but what is happening is that alteration is causing a change in the outer layer. We can see the velocity profile is decreased. Okay, so when the velocity profile, the magnitude of the velocity profile is decreased, because means, so obviously you will have the decrease in the drag. Okay, so when compared with the no slip wall, we are having a change in the value of the velocity in the buffer layer and the outer layer. So this is causing a huge reduction in the drag of the superhydrophilic surface. Okay, so the mean velocity profiles with the corresponding average slip velocity subtracted is shown in this figure. A gradual reduction of the velocity is found to be observed in the buffer layer. So this is causing the higher drag reduction. So the log layer expects a downward shift rate. Okay, so again, you can see that from the buffer layer onwards, we can see that there is a decrease in the velocity layer that will cause the drag reduction. So by increasing, so I can see that by changing the number of the distance between the posts and the ridges, the drag reduction rate is keep on increasing. Okay. So this is the secondary flow structure. What is happening? So I'm having a no slip. This is for the ridges and this is for the posts. And you can see that this is the secondary flow structure, which is causing because of the presence of a no slip versus free slip. And this is causing at a very, very micro level that is happening only in the laminar sublayer. And also, since we are heating at the bottom, we can see that there is a thermal, the appearance of the thermal boundary layer. And also, you can see that there is no boundary layer present. So these are all thermal boundary layer. There is no boundary layer present due to there is no wall in the case of the free slip wall, because the super hydrophobic surface is having a free slip and the no slip. Therefore, there is no velocity boundary present, but only you having observing the thermal boundary layer. Okay. So the lateral motions are confined to the viscous sublayer. This is along the span-wise direction. The vorticities are formed, and protrusions of the mean velocity remains marginal. A well-developed thermal boundary layer is developed, whereas there is no velocity boundary layer because due to the presence of the free slip plastrons. This is nothing but a super hydrophobic free slip surface. So you can see that when you're increasing the size of the super hydrophobic surface, the recirculation region becomes more pronounced, more visible, and it is going means this is affecting up to the buffer layer. That's why we can see that there is a alteration in the velocity profile, which I showed in the U plus versus Y plus part. So the upfast region over the no slip region for larger future wavelengths leads to the redistribution of the streamwise momentum. Okay, so therefore there is an inhomogeneity will be occurring along the span-wise directions. So the secondary motions not only will help in enhancing the mixing, but also it will create that will help the reduction in the velocity profile, means because of the presence of the no slip region, because whatever the friction which is present in the no slip will move to the free slip region, so that therefore the effect of the viscosity is more means we are moving away from the viscous region to the free slip region. So therefore the free slip regions helps in reducing the viscosity. Thereby, your drag is reducing with the increase in the structures, that is from 18 to 70. Okay. So I'm showing only the two limiting cases. This is the lower one and the larger one, 18 to 70. And this is the thermal boundary layer, isothermal contour surface. So near a T is equal to 0.9, we are not seeing any much change because it is very close to the thermal boundary layer. But if you come above to T is equal to 0.7, that is Y is equal to 0.7, we can see the structures, the streaks, isothermal contours are it's very nicely visible. And you can see that in the case of ridges, the structures are not continuous. It is more broken when compared with the posts, where the post structures are more continuous. So that is what we are observing. And also you can see the same thing I'm reproducing. This is the velocity streaks, and this is the thermal streaks. So wherever you are having the maximum velocity, you can see that there will be the minimum value of the temperature. So the blue color represents the minimum value of the temperature, and the red color represents the maximum value. So wherever you are having the red color velocity, you are having the minimum value of the temperatures, which is shown in both the cases. As I told earlier, in the case of ridges, it is not very means it's very continuous, whereas in the case of posts, it is not breaking. So in the square post, thicker, slow moving hot patches interspread with the short and intense high velocity streaks are visible, whereas in the case of the ridges, you can see that a disintegration of the thermal streaks is happening. Okay, so that's we can see that this is these structures are available in the literature. So therefore we have reproduced this one, and we found that the physics is almost matching with our results as well. And when you come with the thermal profile, the temperature profile, and obviously you can see that there is a reduction in the case of temperature profile also, because not all the solid surface is exposed to the fluid because of the presence of the superhydrophobic surface. And we found that a downward shift of the T plus is happening. This is mainly due to the reduction in the surface area of the superhydrophobic surfaces. Okay, so we found that there is a reduction in the heat transfer, But at the same time, there is an improvement in the drag reductions by utilizing the superhydraulic surfaces. This is already studied in most of the literature. And this is the turbulent Prandtl number. So we found that there is a steep decline in the Prandtl number happening near to the wall, but the net Prandtl number is found to be. So this is mainly we have calculated so that the correlations can be satisfied with our the simulations. So conclusions from the first part of the work is, so we found that the Nusselt number is reduced due to the presence of, because the superhydraulic surfaces, we are having both no slip and the free slip walls, and that will cause the reduction in the heat transfer. So the effect is developed at the superhydrophobic surface wall results in weaker gradients of the streamwise velocity. So therefore, we can see that there is a more recirculation is there, but it's not having enough strength to carry the passive scale. And the mean temperature distributions is also shifted downwards because of the reduction in the surface area. And we found that the turbulent Prandtl number for square poles are observed to be less when corresponding to the ridges. And also we found that the correlation is satisfied. The net value of the turbulent number is coming around 0.8. That is turbulent Prandtl number. But within the viscous sublayer, both the square poles and the ridges show a steep drop in the turbulent Prandtl number. So with this knowledge, we went further ahead to find the structure which is common to both ridges, the straight ridges and the square posts, and that is called as sinusoidal ridges. So what we have done is we have created ridges like this with the sinusoidal wave, and so the same dimensions we have given, and this is a free slip and no slip. What we are changing is only the curve, that is the amplitude of this one we are varying, and with this we found which is the optimum to get the maximum heat transfer and the minimum, that is the wavelength we are changing with that wave, which one is giving the maximum heat transfer and also the minimum drag reduction that we have identified from this. And this also we found that this structure is better when compared with the whatever the one which is present in the available literature, and this is developed in our laboratory. There is a novel structure we have developed that is called as sinusoidal ridges. So we have changed the coordinate mapping, and due to the time constraint, I am not going much in the formulation. So this is the simulation case. So what I told is we are changing the wavelength. So we have considered 6 wavelengths. So that is the wave of the sine curve. So this is the wave of sine curve wave. So we have changed from S1 to pi by 2 to S6, that is a 4 pi. And for understanding, for our comparison, so we are also comparing, one is a no slip wall when there is no superheated surface. Other one is we are comparing with the straight ridge. Okay, the straight ridge is more like a sinusoidal ridge. Therefore, we are comparing with our results with the straight ridge and also the no slip wall. And this is the drag reduction. So the drag reduction is given by 2 tau w by, that is tau w by half u bulk square. So that is we are calculated, and we found that the maximum drag reduction, the drag reduction is shown in the means higher, means more the value is the higher the drag reduction. We found that for a wavelength of 2 pi, we found that the maximum drag reduction is happening. So this is found to be better when compared with the straight ridge and the square post. And the slip length also, we found that for a wavelength of 2 pi lambda by delta, we found that there is a minimum slip length is occurring, and the slip length is calculated using this Navier slip conditions. And you can see the velocity profile. So this is the no slip wall and the straight ridge. This is the straight ridge which is shown here. When compared with the straight ridge, you can see that a marginal increase in the velocity profile. Even though there is a marginal increase, there is no much change. There is no much change in the drag value. The drag value is almost in comparison with the straight ridge and the square post. But the main advantage is we have improved the heat transfer performance in this case. And so this is how the recirculation regions are happening. So you can see that this is a free slip and no slip, how the recirculation regions are happening because of the free slip and no slip, not only in the span-wise direction, but also in the case of stream-wise direction. So while moving in the forward direction also, you will encounter a no slip and then followed by a free slip. This causes a more pronounced super means mixing both in the span-wise and the stream-wise directions. So with different variations, we found that how the we can this is the slip means this is the jet is moving here and it is coming here when it is a free slip, and this is the velocity which we are plotting with reference to the y direction, how the velocity is changing. We can see that the sign is changed. The sign is changed from positive to negative. This shows that how the verticity means how the velocity player is changing, and thereby how the drag is getting reduced. Okay. So we also found the spatial Stokes layer, and we calculated how the verticity generation. Verticity is generated here, and this is how the what is generated when it is omega x is less than 0 means it is intensified. When omega is greater than 0 means it is suppressing. So verticity is suppressed and intensified. So we found that moving in the streamwise direction and in the spanwise direction, the verticity is intensified and the suppressed. And this is the streaks, velocity streaks. This is the straight ridge, and these are the different sinusoidal ridges. 6 cases: S1, S2, S3, S4, S5, and S6, and how the vertex structures are helping in improving the drag reductions that we analyzed in detail. And again, the same way how the temperature controls are also observed in this. We also observed here. And these are the Q criterion. This is the turbulent structures. So we found that for S1, it is similar to the straight ridge. But when you see the S2, S3, S4, etc., S5, S6, etc., we found that a huge amount of structures will be created, and that will help in that shows the pronounced mixing, not only in the streamwise direction and also in the span-wise directions. So with this, I'm concluding the talk. These are some of the main conclusions. We found that the sinusoidal, in a nutshell, the sinusoidal texture is more advantageous in terms of, although we can compare the straight ridge and the sinusoidal ridge are comparable in terms of the drag reductions, but we found that there is an enhancement in the heat transfer takes place because of the sinusoidal ridge. Okay, so this is the last sentence. The heat transfer in the sinusoidal ridges superior surface are found to be improved when compared with the straight ridges and the square posts superior surfaces. So this can be utilized not only for the drag reduction study, but also we can use it for somewhere where we can for heat transfer enhancement studies also. So that's what our conclusion. With this, I'm concluding my talk. Thank you for your presence listening. These are some of the references. I'm acknowledging all the my students and the collaborators and the supports from the various agencies. And this work is done mainly as a part of my PhD work from my student Fuad. So this is a Fuad right now. He's in Finland as a postdoctoral student. So this is PhD work. I'm presenting that work. Thank you everyone for passionate listening. I'm happy to answer if you have any questions.
Thank you, sir. The session is open for any discussion. Any questions? The chat box is live now. You can post your questions in the chat box, or you could unmute yourself and ask a question.
Hello, Adil sir.
Yes.
Hello, sir. Am I audible, sir?
Yeah, it's audible.
Sir, I'm Jaydev from SCMS College of Engineering, School of Engineering and Technology. Sir, I have a doubt on this analysis because if we are using this hydrophobic surfaces, how we can control the Vidya ma'am, somebody's mic is on. Can you please tell to unmute?
I have muted it.
How we? Okay, thank you. How we can control this because it has great dependence on contact angle, right? And also this ridges also will give some kind of resistance to the flow, right? That also will take care of, right, when we are calculating this this resistance and all. how we can
See,
incorporate
basically,
that, especially
see,
the profile.
no, that's what I'm telling. This is this structure is something like it's very micro or nano level. Okay, you cannot see you cannot visibly see these structures. Understood? When you see a lotus leaf, there is a supernodal surfaces embedded on the lotus leaf. Whether you can see the structures on that, it is not visible. But when you put the water, so the water will flow smoothly on the lotus leaf also, but it will not stick to the leaf. That is the main motivation here. But it will not create a huge frictional resistance when compared with some. You can see that you have a roughness on the wall, etc. So this one will not create any sort of frictional resistance, means drastic frictional resistance when compared with the other surfaces. Therefore, the ridges and something like this is a very small. It's order of 0.1. Y is of the order of 0.1 only. So this will not create any much resistance. But this will, and since it is not sticking, it is creating a resistance between the solid wall and the fluid. There is an air resistance between these two. So that will cause a reduction in the velocity profile, which in turn will decrease the drag. That's the idea. Whether I answered your question?
Jadhavan sir, is that clear for you?
Yeah. Also, between these ridges, there will be an air cushion, right? There will be trapped air, and it will give some kind of.
That is the novelty of this work.
Okay.
So this we are creating purposefully air gap and interface. So this will create a small mixing between the no slip and the free slip.
Okay. So if it is there, is there any vortices will?
That's what I showed.
Vortices will generate or.
Yeah, that's what I showed in the. I showed it in the. So this is also, you can see that. So this is the vortices. There is a upfilling motion, and it will come down as a downfilling motion. So no slip fall and the free slip fall. We can see that this is extra. So it is going up and then coming down. Yeah. The vortices are available here.
Okay. Is it because of some?
You can see
is
that.
It kind of?
Sorry.
Is it because of some kind of temperature difference, or there's a buoyancy effect and something like that?
No, this is mainly now.
This fluid motion is happening.
This is mainly causing because it's a turbulent flow, and this is mainly the due to the interface. There is some there is a free shear between the no slip region and the free slip region. That is the main reason, and this will help in improving the mixing. So this is this I'm showing not only in the I'm showing in the span-wise direction, but not only in this free slip and no slip interaction will happen in the span-wise direction, but also in the stream-wise direction also.
Okay, sir. Thank you. Thank you, sir. Okay.
Any more questions? Sir, it truly was a wonderful and informative session.
Thank you.
Thank you so much. Now I invite Mr. Joe Shedril Dikota, Assistant Professor, Department of Mechanical Engineering, ICCME School of Engineering and Technology, to propose a word of thanks. Over to you, sir.
Thank you, Mr. Sanju. Good morning, Professor Dr. Adil Prakash, and all the professionals in this colloquium. It is my privilege to have been asked to propose a vote of thanks on this keynote session. I, on behalf of AICT, sponsor Third International Conference on Computing in Mechanical Engineering, organized by ICCME School of Engineering and Technology, and let me call it fraternity of researchers and scholars here together. And on my behalf, extend a very hearty vote of thanks to Professor Dr. Adil Prakash for sharing with us his novel observations on turbulent fluid flow and heat transfer characteristics over textured superhydrophic surfaces. It was quite inspiring and contained all the essence to trigger the mind of a researcher to understand the importance of analyzing the fluid flow based on numerical studies. Thank you, sir, once again for sharing your valuable time with us. I also take this opportunity to thank each and everyone here for being a part of this conference. Thank you, sir.
Thank you. Thank you so much.
Arul sir, how are you?
Thanks, sir. Good evening, sir. Hi, sir. Good morning. Nice to see you. Yeah.
Yes, sir. Yes, sir.
So,
When you are coming, sir, when you are coming to our side,
soon, sir. Very soon. We'll see, sir. Yes, sir.
please inform, sir, once you come over to Madurai or someplace, or
Sure,
we'll find an occasion to invite you.
Sure, sure.
Like
Sir. I'll let you know, sir. I'll let you know, sir.
Now you are free to travel, sir.
No, sir. Right now we are having a JEE, and maybe that is going to happen next week. So we are going with the travel restrictions, and after that only we'll see the impact of JEE.
Oh,
So many of them are coming to Kerala also. Yeah.
Right, sir. Thank you, sir. Thank you.
All the best, sir. Okay. So have a nice talk. I think your talk is scheduled at 10 o'clock, right? Yeah. Okay. Okay, sir. Thank you. I'll take a look.
Thank you, Adil Prakash, sir.
Thank you, sir.
Shekhar sir, good morning.
Good morning, sir. How are you?
Good, sir. Good.
You are here. Very
Yes,
nice
sir.
to see you.
You too,
Oh,
sir.
great, great,
After
great.
a long time. Yeah. Hope you're
Yes,
doing
yes.
good, sir.
Good, good, good. Oh, I never expected you. Great to see you. Right, sir. Right,
Yeah,
sir.
I'm very pleased to see you, sir, again.
Yeah, welcome, sir.
Good morning, Chair, sir. I'm
Sir,
glad.
good morning.
Okay, okay.
Nice to meet you, sir.
Thank you, sir.
So Dr. Rag is our head of the department, mechanical
Oh.
engineering.
Oh, great, madam. Nice to meet you, sir.
Thank you, sir. Thank you.
Shall I share my screen?
Vidya ma'am, shall we start the session?
Yes, Sanju sir, please.
Ladies and gentlemen, we are moving on to our fourth keynote session. Before we move to the next keynote, let me kindly request you to fill in the feedback through the link posted in the chat. Now, I invite Dr. Rag RL, convener ICCME 2021, professor and head of the Department of Mechanical Engineering, SEMS School of Engineering and Technology, to welcome the keynote speaker. Over to you, sir.
Sanjay sir, am I audible?
Yes, sir, you are.
Okay, thank you. Respected keynote speaker, Professor Dr. M. Shekhar, other dignitaries, and dear participants. A very good morning to all of you. We are in the last keynote session of ICCME 21. Surely we can say we are enriched and enlightened by the last 5 keynote sessions and the plenary session. It gives me great pleasure and privilege to introduce and welcome Dr. M. Shekhar to this keynote session. Dr. M. Shekhar holds the current position of Principal, AAA College of Engineering and Technology, Shivagashi, India. Formerly, he held the position of Head of the Department, Mechanical Engineering at Karunya Institute of Technology and Sciences, Coimbatore. Dr. Shekhar had obtained his doctoral degree from Kyunbuk National University, South Korea. He was awarded the prestigious Korean Research Fund to carry out his research. His research interests include computational geometry, motion control of CNC and robots, stability analysis of machining processes, and industrial IoT. He is a fellow of Institution of Engineers and active member of several professional bodies. He has published more than 70 research papers in reputed international journals and conferences. He has 2 patented inventions to his credit. On behalf of the organizers and participants of ICCME 21, from the bottom of my heart, I extend a warm welcome to you, sir. I also welcome all the dignitaries and participants to this keynote session. Thank you all.
May I proceed, sir?
Yes, sir. Yes, sir. Yes, sir.
Yes, sir.
Definitely.
Yes, sir.
Yes, sir. Over to you, sir.
Good morning, my dear fellow colleagues and researchers. The next 1 hour or so, I would like to spend some time on one of the important aspects related to nerves, especially from the computational side, because our international conference is mainly on the theme on computing in mechanical engineering. At this moment, I thank Professor Dr. Rag for his welcome address and introducing myself, and I thank the other members. Please interrupt if my voice or is not audible, because I'm from a little bit remote area. So if there is any delay in voice or something, I request Vidya Madam to please let me know through WhatsApp so that I can check. At present, I have nearly 4 towers, so I don't think it will be a problem, right?
Sure, sir.
Yeah. Today I will be touching these 6 important factors, and in the research direction I will be introducing, or rather I would like to discuss with the researchers and let you know about the various prospects in this research, especially in the area of nerves. First, I would be spending some time in how the freeform design geometries are represented in CAD and manufacturing. And now what is the trend towards this generalization, that is by using nerves, how it is generalized, and what are the issues with manufacturing the freeform shape. There are a lot of issues, both computational and implementation issues, and I will explain the computational issues and solutions, and some aspects on implementation also I will discuss. The machining dynamics part, if time permits, I would like to add, right? So all these are potential research problems for many of the faculty and research members who are watching this session. Okay, this is one of the model that I have taken from Alias model from this Autodesk software. This is a pure 3-dimensional model which they have developed using the freeform curves. Those who are using softwares like CATIA, we all know about when we enter into surface model, we use a lot of different shapes and curves, and we design this geometry. So nowadays, these geometries are so popular because the automobile and the consumer products and especially the tool and mold design, they need such very complex shapes. So the CAD has been developed because it is relying on the power of the computer, and with the latest developments, these models can be easily built with the latest softwares. One of the most important software that most of us know is CATIA and Autodesk Alias. There are several other softwares in this area. In due course, I will introduce that also. Now, what happens here? When we design a model, for example, an aerodynamic model like this for a car, we want to design it very smoothly, and it should not be approximated by means of certain small linear segments or the so-called a combination of small straight line or curvilinear sections. Instead, we want it to be a very smooth representation. So this is possible with some curves like curves and surface representations like NURBS, or simply we call it as B-splines and Beziers, which we usually learn in mechanical engineering, computer graphics, and in computer science also we learn in computer graphics subject. This subject is widely called as this subject is covered under a widely known subject called as computer aided geometrical design. There is a separate journal under this topic where we can find very useful information and very useful journals in this area. So now seeing this car, we can find all these segments are beautifully designed. These surface segments are designed with a single or multi surfaces where some patching is required, which is done by a experienced designer, right? Now, how these complex geometries are represented? Normally, the representation is done by means of two methods. One is called as explicit representation, and another is called as implicit representation. For example, if we use a line and we can calculate the explicit value of y, that is the y coordinate value, by substituting an equation, like for example, an equation for a line mx plus c. We directly give an input x and we can get an output y. But in implicit case, it is not like this, where you often go for a parabolic, often go for a quadratic equation or a cubic equation where you solve. Mostly for conics, we go for quadratic equation. All the circle, parabola, hyperbola, ellipse are represented using implicit way. Of course, using the implicit way, you can convert that into an explicit representation. The advantage of this explicit is that we can't help with two values. It should give, if two values are obtained, where to locate will be a problem. So we directly go for implicit representation when we have multiple values x, y, z. Okay, x, y, z axis. If you want, then we go for such implicit representation. And all these representations can be done in two ways. The first one is called as algebraic representation, where we use an equation just we have explained, I have just given in the previous slide, by using the x and y coordinate directly, so that a mathematical expression can be derived. However, in case of a parametric representation, we go for a parameter. It is called as a dimensionless value. We call it as t, or we call it as u in most of the cases, or theta in most of the cases. So as a simple parametric equation for a circle, we can define with a value called theta. X is equal to r cos theta and y is equal to r sin theta. That is one of the advantage of representing using parametric representation, because you can define the x, y, z vector. You can denote the coordinate as a vector, as a single point, ti vector, where you can derive this with the help of a single variable called parameter variable. That is the biggest advantage. The advantage is that you can easily extend to 2, 3, or in case of homogeneous representations, where we can use for perspective views and other views. And a closed curve can easily be determined or defined with the help of this parametric expression. With the help of parametric representation, one can go for transformations. The algebraic curve always has some problem when we rotate and move from one coordinate to another coordinate system. We call this as affine transformation. Affine transformation is easy in case of parametric representation, where we can use local coordinate system. However, in algebraic, when we use algebraic representation, we need some more mathematics to support that. So for all these reasons, the parametric representation has become very, very common in all the CAD softwares. Indirectly, in all the software kernels, the CAD kernels, what they use in softwares like CATIA, Parasolid, or Autodesk, they represent these things with the parametric way. Right now, free-form geometries, the difference between the previous one and this is the free-form geometry is will be controlled by means of something called as control points. The control points define the shape of the curve. This was first done by Bezier when he designed a car, and he made this smooth representation with just 4 control points. You can see that diagram. And by moving the control points, the polygon which gets connected by these control points alters, and the entire curve also gets altered. The problem with Bezier is that suppose we want to have more control or more accuracy, we need to increase the control points. And increasing the control points increases the degree of the curve. Like when we know that when the degree of the curve becomes more, it becomes difficult to implement computationally. In all computers and other places, we go for second and third degree of curve, which will be easy for us to work both in CAD and CAM. Especially in CAM, going for higher degrees will be always troublesome, because we have to complete everything within a very short time, what we call as sampling time of the controller, right? So this sort of representation that is free from geometrical representation, where we can control with the help of, where the designer can design smooth shape with the help of control polygon, has become popular for the last 30 or 40 years. And further improvements are being done. Actually, the algorithm was developed by one French engineer, so called as mathematician de Castellet, and instead, because his thesis was not so open to the public, we call it as Bernstein basis function. So whenever we draw this curve is of this Bezier or B-spline or the curves that we are going to see now. So now how it can be generalized to NURBS, that I will let you know. Am I audible, madam?
Yes, sir. You're audible.
In computer-aided geometric design, the basic freeform geometry is by means of Bezier, which was further improved by another type of curve called as B-splines, and now we are working in NURBS. So what are the important components of this curve? The important components of this curve are control points, knot vector, weight vector. And we will see the global control and the C1 continuity or C2 continuity in the next slide. Now, having understood the simple basics of Bezier, what is the problem with Bezier when we want to go for a bigger shape like car? Like the car entire model, if you want to do, then we have to split this shape into different curves, and we have to join these curves. Like the one which I have shown here, this one, sorry. The first one we call it a single span. 3 single spans put together forms a geometry that is given in the first figure. And in the second one, we call it as multi-span curve. It is a single curve where we introduce something called as spans, and these spans are defined by a vector called as knot vector. That is the purpose of knot vector, where we can individually adjust the span. For example, the span 1 can be individually adjusted, span 2 can be adjusted, span 3 can be adjusted, though it is a single curve. That is the biggest advantage of this B-spline curve. In Bezier, we cannot do that, and hence it is called as global control. We cannot control the curve in a particular point. If you want to control, then the shape of the entire curve or surface will be changed. However, in case of B-spline, it is not so. We can have global as well as local control. This local control made B-splines very, very popular. And a simple modification was required in B-spline. The modification is that they made it rational. What is rational? Rational means a curve will have both denominator and numerator. So far, the Bezier and B-spline had only the numerator functions. Mathematically, a rational curve can describe a conic section. Otherwise, it is not possible. So they went for a rational curve. Then the next slide, I will explain that. So that with the help of rational curve, it is possible for a B-spline to represent any type of geometry. For example, we can represent a circle, we can represent a line, we can represent a parabola, we can represent any type of curve, any type of surface using a single entity or by means of a combined patch surfaces. Right now, how we compute the coordinates of the nodes? I'm not dealing much with these shape functions or the piecewise polynomial functions. We call it is all available in standard textbooks. I will give you the textbooks also. This n is called as rational function. N of IP is called as rational function, where this is a recursive function. Now, this polynomial function is, since it is recursive, it can be very easily implemented, and compared to a Bezier curve, it requires fewer points for higher degrees. So this sort of curve, B-spline curve, is very widely used, and when we express this in a rational form, it becomes NURBS, that is non-uniform rational B-spline curves. I will explain what is non-uniform. The knot vector, what we define in this case will be, in a general case, will be uniformly distributed. For example, if we say the knot vector 0, 1, 2, 3, 4, 5, 6, etc. So the difference between these values 0 to 1, 1 to 2 is fixed. It is called as uniform vector, and non-uniform gives a more control to a particular place. It gives more local control to particular space. For example, in the previous slide you have seen, there was a curve, and we can increase the number of knots there so that it can be easily adjusted. Right. So this helps to define complicated geometries for CAD. So that's why we call it as non-uniform rational B-spline curves. Right. That is a basic thing that I want to tell. Now, with a single definition of the curve, we can go for different functions. See, the C of U is the curve. C is a vector valued function, which means that if it is a two-dimensional value, when you input the parameter U, which is normalized from 0 to 1. In the earlier one, which I have told, the knot vector can start from 0, 1, 2, 3, 4, 10, etc. Whatever may be the case, we have to normalize it for while calculation so that the value starts from 0 and ends with 1. PI is the control point that is defined by the designer, and U is and N of IP is the shape functions or the rational basis functions we call, and the C of U is the actual coordinate points. If we have a two-dimensional geometry like X and Y, we'll get C as X and Y vector. And if it has 3 dimensions, we'll get X, Y, and Z. And if we want to convert that into an homogeneous coordinate, then we have X, Y, Z, and the homogeneous coordinate representation also. And the one which I have shown on the right side, or for you, it may be right or left, the curve is defined by the control point where you are getting something like a tie knot, right, or a shape called 8. This is the rational function, and you can find different rational functions, different N of IP in different colors. It starts from 0 and one ends with 0.2 or 0.25, and the other one starts. Wherever we count, wherever we summarize, we always get the value of 1. For example, if we take U at U point U, the parameter U 0.2, and if we summarize the value, if we sum the values of the coordinate of the rational basis function on the y-axis, we always get 1. That is the mathematical reason behind this rational function. Right now, I change certain weights and other things. You can find the shape further moved towards the extreme points. Right, it has almost become a something like a curved 8, and the one which I have shown on the other one, it has become almost or it has become a straight line. See, earlier we started with a curved shape. Now, with the same set of values, by changing the weights, one can make this into a line. So this is a classic example that I would like to tell, that nerves can be used to represent lines, used to represent any quadratic geometry and any other curves. Right, that is the advantage of nerves. So here the values that I have given is 25, and here 100 I have given the value. Just a minute. Now, what are the issues with nerves that I will tell? Now, all the major CAD softwares are standardized with something called as nerves. So I have shown the first one with the Autodesk alias, where they have made a chimney that is the lantern with using this model. The next one is the Rhino software, where they are using this for 3D. And for robot planning, there are several obstacles, and it can be approximated. We call it as path optimal algorithms, so that you can approximate with a certain shape called nerves, right? So you can find both the line segments as well as the curved segments also. Now, it is widely used to represent, suppose we want to machine an exact part using the conventional CAM, it is not possible. I will explain in the next slide. It is used in robot path and trajectory planning. Now, what are the problems here? The problems is mainly due to the computational complexity of this NURBS curve. That is the most important problem. The other problems, segmentation and other problems, can be easily overcome by improving so-called something called as CORD error, COHROD, CORD error. So there are different types of errors that we follow. We have to follow in CNCs. The most important part is the CAD CAM error that is generated by the toolpath CL data file. And we call it as chord error and feed rate error. The other type of errors are set with the hardware. The first one is called as basic length unit error. For example, if you have a machine of very fine resolution, BLU will be very less. You cannot control the machine with error less than that value. And system error is what we call as following error. Following error means, suppose I command the machine to go to a certain point XY, and if the machine goes X plus delta X and Y plus delta X, and this difference is called as following error. And when we calculate it for a contour, not on a line, we call it as contour error. And when we integrate with machining dynamics, we have vibration, errors due to chatter, errors due to thermal variations, that is temperature variations. And structural error, we have something called as deformation error due to cutting forces and the geometric errors. So all these errors can be studied, but however, I'm going to concentrate only on the first part because it is more computationally intensive. The others are hardware dependent. No, these are the basic so-called interpolation types. First one, the point-to-point type, and the linear interpolation and circular interpolation, and we have parabolic now. We have also helical involved in our modern computers, modern CNC machines. And in most of the cases, we go for linear and circular motions. Point-to-point motion is used for G0 or the rapid motions. Helical and other things in 5-axis CNC we use. And most of the conventional controllers do not have something called as NURBS interpolator or spline interpolator. So it always go for some approximation. So what is approximation here? The actual toolpath is shown in the diagram. And now when you approximate this with the help of linear segments, because the machine cannot follow a circular path, machine always moves along X and Y axis, because you have X table, Y table, and Z table, and it always moves along a linear path, where the size of the linear path, when it tends to 0, it will follow a circular path. So if you want to make a more accurate shape, then we have to reduce the chord error. Then the number of line segments will be more, so that the actual toolpath can be represented. Now, DNC is distributed numerical system we can use. Why we use DNCs? Because when a NURBS curve needs to be approximated with n number of linear segments, n can be more than 1 lakh. So we need G0 1 lakh statements. A controller normally has limited memory and it cannot store. So what we do is that we have some direct numerical control where we can pass the G codes by means of a computer, and it goes to the memory of the controller. There it takes. This is how normally the Mastercam and other softwares work. And for each and every linear interpolation, that is G01 to next G01, there is a small dwell period which occurs due to the parser. In every CNC system, there is something called as parsing, and this parsing has this effect. And this dwell period and the rate at which transfers are limited to the hardware of the CNCs. Though the latest CNCs employ very good processors and other things, still we have problems, because now the aim of manufacturing has become more and more stringent. We want accurate more and more. We want to machine more and more accurate products of complex geometries. Now, what happens when we have a number of straight line motions, which is very short? The actual profile we follow is a trapezoidal profile. But when it becomes very short, when we have no time to have this constant profile, it becomes a linear, it becomes a triangular profile. And the machine moves from a lower feed rate, immediately goes to a higher feed rate, then drops down. And when we have a series of triangular motions like this, the machine will start to vibrate, and the controller stability is also questioned, and the machine tool stability also gets into problem. So to overcome this, we need something called as look ahead algorithm. I just go to the next one. The effect of short segments require something called as look ahead technology, which means that which is available with the code in modern codes like G157 and other things, where the processor, where the computer process, where the NC kernel can oversee somewhere around 100 or 200 or even 500 blocks, and it will plan accordingly. This is something what we call it as, suppose you are traveling along a mountainous route in say in Kerala, where you have a lot of mountains, and there are so many corners, and suppose you know these corners, you will slow down your car based on the forthcoming sharp bends, right? In the same way, this look-ahead technique works in CNC control also. And this is becomes an important critical factor, because the processor has to spend some time, which is called as BPT or block processing time. So normally in a control system, the time spent for calculating the interpolation algorithm and the control loops and the feedback loops are very important. And suppose we overload this with this BPT, that is block processing time, it becomes the controller accuracy becomes reduced. So this time should be we should be careful with this. That's why most of the controllers go for 100 to 250 blocks. Now the solution for all these things occurs by means of parametric interpolation, where we directly go for parametric improvements. So these are the three types of parametric improvements that we can say. For example, in the initial slides you might have seen, that is a C of U, a curve of U parameter can be obtained by substituting U value. When we increase this U based on say 0.001, suppose the U value is 0.2 plus 0.001, that is delta U, if we make it is constant, we call it as constant parametric value. And the next one is based on Taylor expansion method that we are going to see now. And in case of curve modification, we just modify the curve into some different form of curves, like we bring back to quintic splines or Pythagorean hodograph, or the conventional method of approximating into n number of linear segments. This is how the parametric domain works. For example, there is a curve which is shown in red line, and there are parameters, for example, different parameters u1 to u2, u3, u4, maybe n number of parameters. And if you want to compute uk1, say for example, suppose our u parameter value is 0.1, which corresponds to x2, y2, z2, then we just add with delta t into the differential term of du by dt. This is the simplest form of Taylor's interpolation series, and for computational complexity of higher order derivatives, we remove the higher order terms. Why? Because we are going to use this in CNC machines. Higher order differentiating higher order terms of a complex NURBS curve is really computationally intensive. One important thing that we must understand, we must note, is the non-linear relationship with u. For example, there is a graph which is given in the right side. Some may say that, sir, if I know the length, can we parameterize it? No, it is not possible, because for a given u value, the length cannot be computed because there is no closed loop solution. What is closed loop solution? For example, a circle is there. If we want to find the circumference of the circle, we say it as 2 pi r. In a NURBS curve, there is no such formula. So we cannot determine the length of the curve by just giving a parametric value u. So it becomes another complexity. So we have to work on two domains. One is called as parametric domain, and the other one is called as time domain. The time domain plays an important role in actual realization of the curve in deterministic machining processes. Right? Now I have told this, so I skip this. Now, how we compute the feed rate? By introducing chord error. Earlier, we have seen the chord error concept. Suppose we want to move the machine at certain velocity. How the chord error can be related? Suppose we have the chord error is a system dependent, means it is hardware dependent. You can code in the hardware by taking some value that is called as del max. And by inputting this value, one can find the feed rate at any given point of the parameter by using this formula, where Ts is the sampling time and rho k is the instantaneous radius of curvature of that NURBS curve. So the differential properties of the NURBS curve is very important here. First, to calculate the curvature, we have to differentiate it twice. We have to compute the tangent vector. Then from the tangent vector, we have to compute the curvature vector. And whenever curvature changes from one direction to another direction, we call it as inflection point. That inflection point also matters a lot while machining a curve. Right? Now, how we reduce the curve, how we reduce the chord error with respect to time, you can find in the two graphs by reducing the feed rate. One can reduce the chord error that was shown in the diagram. So whenever there is a sharp corner or a sharp curve or a cusp, we call it as cusp, the machine has to slow down so that the chord error becomes minimal. So when it slows down, so automatically the velocity of the or the feed rate of the machine also should decrease. So this algorithm gives that how to determine the feed rate at any given point u, and this is dependent on the second derivative of the curve that is called as curvature. That can be obtained, the radius of curvature can be obtained by the second derivative. So this is the curvature analysis. So whenever the feed rate goes down, it means that we have reached a point and we have to slow down the machine. And this point may be corresponding to the sharp corner or a cusp in a surface geometry or in a curve geometry. Now, I have drawn a simple open NURBS curve, and the rational basis functions are given here. The data points, control points are given here. The north vector is given also. Now, you can find the curvature vector. See, the red one is the curvature vector, where you can find the curvature, the curvature vector moves from one place to another, especially from the arrow which I have marked. The curvature is on the right direction, and when we come down, the curvature is on the left direction. It means that when you travel along this path, assume this is a mountainous path. When you travel along a car, you are steering, you will be driving with your steering in one direction, and the other point you have to move to the other direction. So in the same case, if the tool movement is done without any smooth process, the tool will break. So these are the internal complexities that we never understand, because we just follow the CNC G codes, and finally we come with a blunt tool, and no one knows why this tool has blunt suddenly, right? These issues often the machinists know, but it will come through the CAM code, the code generated from the CAM software. So such points are called as inflection points, where the curvature changes from positive to negative. At this point, though it looks smooth, your machine tool or the machine control should slow down the machine. It should know where this curvature comes. Such intelligence must be built or coded in the G code itself. So I have simplified this. Let us go to something called as feed rate error. Now, feed rate error is the one which we must understand. Feed rate error means, suppose there is a segment, a linear segment, and this linear segment ends with 10.2, where your command can move only with, where your increments with respect to the time can produce only 10 divisions. For example, if it is 10 mm, it will go from in the first sampling time, it will go to 1, 2, 3, 4, 5, 6, 10. You can convert this into microns or nanometers, but it will leave the 0.2 because the next one will be 11. This 0.2 creates something called as feed rate error. It can be either 9.8 or 10 or 10.2, because the number of increments is dependent on the sampling time. The sampling time determines, and the basic length units also is an important factor, that we call it as the machine part. Suppose we assume the basic length unit is very, very close, this issue will not come, but the sampling time plays an important role, and because of the sampling time, the machine tool will be commanded either to a part which is either to a point which is 9.8 or 10.2. Sorry, to 10 instead of 9.8 or 10.2. If the desired coordinate is 9.8 or 10.2, it will reach only 10. This creates something called as feed rate error, and this has to be avoided. And in normal process of G01, this cannot be avoided. Please note that, because the number of increments n is an integer, and we cannot avoid this. How we can avoid using parametric interpolator is the next topic. Now, we can reduce this feed rate error by adding the higher order derivatives. That is the second derivative, that is u, second derivative to u, and the third derivative to u. You can find this, which I have shown in red arrows. When you increase the number of derivatives, what happens is that the feed rate decreases, but the computational complexity increases. It is a recursive algorithm, and it takes a lot of time. The simple method is proposed to add a correction factor with the value of v, that is shown in the next slide. See what we do. So the zeta value is added to the parameter, not the velocity. So if we want to compute the next increment value of uk, it can be obtained from the quadratic equation a zeta square plus b zeta plus c, and if we solve the positive value of zeta, if we add to uk, then we will get the the feed rate value or the refined incremental value of u, so that the feed rate error is reduced. I have given this feed rate. You can find the feed rate value has drastically dropped in the second in the extreme curve of this pendant nerves curve. In the pendant nerve curve, you can find it consists of both a linear segment, something like parabolic segment, and other things. Right? I will go to the aspects of implementation. Madam, do I have time? Right. Now, I will.
Yes, sir. You can proceed. No problem.
Yeah, I will just rush a little bit fast. See, there are three types of CNCs currently we are employing. The conventional CNCs, most of you know, and the other CNCs is the external motion control board. Normally, this is called as PC-based CNCs. Right? The PC-based CNCs operate with real-time operating system called RTOS or Win RTX, right? Win RTX, and there is something called as Open CNC. Nowadays, it is getting developed where you can find the open source, like Linux Open CNC is available, and some other Open CNCs are available in the market. Now, how we implement in real time? See, there are different type of implementations. One implementation is through MATLAB, and here is where we use something called as real-time workshops. See, most of the mechanical engineers may not use this real-time workshop. It is a very simple tool where if you have a target board, for example, the target board, you can use DSpace or Delta Tau or even Arduino or Raspberry Pi. Whatever code you write in MATLAB, when you specify this on the real-time workshop, it becomes the code exported to that particular controller or particular target board. We call it as target board. Now, after implementing, one of the implementation that we have found is the time which is less than 0.005 second. See, the entire algorithm, control loop, everything is executed in 0.005 second, which is very good. So this is one of the test bed results that I would like to show. And we need a separate data structure for this also, and this is also specified. And some of the machining results that I would like to tell, the circle is generated, a complex butterfly geometry, and a combination of a parabola and line is also generated with this, all with a single curve. Please note that this is a single curve. So I skip this for the want of time, right? I skip this. Just I'm coming to the directions for future research. The most important part in the research is that you can develop your own interpolator, and we can generalize the interpolator. I will explain all these things. And time optimal solutions we can go, and how we can represent nerves in an alternate way. And now the emerging techniques called ML techniques that we can go. Excuse me. I think Madam, can you see my screen? Is it?
Yes, sir. We can see the research directions. Is
it blinking? Something like no?
No, nothing is there, sir. It's good.
It is good, right?
Yes.
Okay, right. Because in my screen it starts to. It is not stable, right? Now I will explain this. So this will be useful for future researchers. Now, in India, from the Indian perspective, because most of the faculty members and researchers are attending from India, in India, we are not doing such research, or the amount of research in this area, especially in CAM, is very less. Why? The important reason is that it requires both your knowledge in mechanical engineering. You must know about machine tools. You must know about something about computational geometry, and you must know about controller and some coding work also required, basic C and other things. It requires a multidisciplinary approach. So one cannot do all these things if you are not a programmer. You will find very difficult to manage this. And also the literature, plenty of literature is available, but you will not find the source code to generate a NURBS. Even if it is available, that NURBS source code cannot be used for any of the applications. You can there are three important books you can refer for this for research in this direction. The first one book is called as the NURBS book by Pagel. It is one of the Bible for this, where you can find the entire source code for generating NURBS. But we must be careful to implement this when using C++ or Python. The entire code is given in C. It is basically pseudo codes where you have to properly implement. The second one, if little bit theoretical understanding, you can have Farin. There is one author called Farin, Farin. You can use his book. And the machining, the dynamics part that I have not covered, because one important point in the dynamics is that most of the dynamic study, the forces, calculation of forces chatter is done only for straight paths. For example, if you mill a straight paths, the mathematical analysis is available only for straight paths. You cannot go for a complex curved path. We know that NURBS is a curved path, and there is no solution for that. In my slide, I have discussed how to find a cutting force when we travel along a curved path, and how it affects the stability conditions of the machine is important. If you want to know about that, there is a book written by Tlusty, Tlusty. The basic fundamentals are available. He has given some codes, and you can start using that, and then you have to develop this. The third book regarding this is Theory of CNC Systems. These three books will help you, will give you a very good knowledge on whatever I have done so far. The major results what I have obtained is through MATLAB and C. So the hardware implementation is done on C. Whether now I'm working on Python, I want to convert all these things into Python so that it can be used. And now coming to the research, I have told the information. Now coming to the different solution for research, the interpolation, every year I can find 10 to 10 papers in at least journals like International Journal of Machine Tool and Manufacture, Advanced Manufacturing Technology, and CIRP and ICCME journals. Every year, in every issue, I find at least one journal paper related to NURBS, machining or NURBS, something is there. So it is mostly focused by Chinese, Japanese and Koreans, Germans, and some Americans. The Indian part is very, very less. So it looks very promising for some of you. If you are interested in coding, if you have friends from computer science and electrical, you can start working this very easily. You can publish paper in less than a year or so. And then the controller dynamics, I have not included so much. You can add the controller plant, the control system values, and you can check. You can even simulate the following error. Suppose you know the plant, you know the lead screw, you know the dynamics of the machine tool table and other things, servo motor and other things. If you easily make a Simulink model, then you can find the following error, and this following error can easily publish as a paper. Lookout planning, lot of work is being done, different algorithms they are proposing, and time optimal solutions for computer graphics and machining. In the so far topics that I have just touched, we have covered only a standard solution. There is no time optimal solution. For example, if you want to reach from one end to another end within certain velocity, within certain chord error, within certain time, is it possible? That is called time optimal solution. This is very much essential for robot. For example, if you want to travel from one point to another point through a different set of obstacles, which I shown earlier, at what time you can reach without the manipulator overshooting the desired path. So this you can study. And interpolators, generalization of interpolators, now I'm working on it. We want to make a single interpolator for all, that is for G0, G01, G02, and NURBS interpolator. All these 4 interpolator, we want to make it as a single interpolator. So I'm working on it. The implementation issues are there. Then alternate representation of nerves, how to improve the line segment accuracy, and some algorithms based on digital image processing that some of you can do. And nowadays, this machine learning and deep learning and neural networks are very widely used, and our Indian researchers are working on it. And some of you can use this to develop solution for nerves construction and for nerves machine. One important thing while we use this machine learning and other thing is that we have multiple values of nerves. For example, if you take circle, we have 2x and 2y common points. Whether the deep learning algorithm will produce different results for a different set of weights, these things you can explore. Of course, I am also working on it. So these are n number of research directions that I can give to the aspiring researchers who are watching this session. For sake of simplicity, I have not covered the 100% mathematics or computational aspects. I have given the simple formulas, which you can find in some of my papers, which I have published in 2016 and 17 and 18, and one old paper in 2008. Now I have come to the point of saying thanks to all of you for your patient listening. It is almost 11, which I have taken 1 hour or so. I thank the organizers of this third international conference on computing in mechanical engineering for giving me such a wonderful opportunity to present this rather unexplored area and present it to the aspiring researchers who are attending this conference. Thank you, madam. Now, if you would like to have some questions, I am glad to hear. I'm glad to answer.
Thank you, sir. The session is open for any discussion. If you have any question, you may please unmute yourself and ask a question, or the chat box is live now.
You can leave my number, sir, and my mail ID. If someone is interested to call me, or they would like, please let them talk. I'll give some directions.
Sure, sir. Sure, we will do that, sir.
One of the easiest area where you can publish papers.
Yes, sir.
Yes, sir.
Yeah. Now I invite Dr. Vidya Chandran, Organizing Chair, ICCME 2021, and Associate Professor, Department of Mechanical Engineering, ICCME School of Engineering and Technology, to propose a word of thanks. Over to you, ma'am.
Thank you, Sanju sir. May I take the privilege of thanking Dr. Shekhar sir. Respected speaker, Dr. Shekhar Mohan, Professor and Principal, AAA College of Engineering, Shivakashi. Dr. Rag, Head of the Department, Mechanical Engineering, SSCT. All other dignitaries, researchers, and dear participants, a very good morning to all. It is my privilege to thank Professor Dr. Shekhar, who is my research supervisor for PhD, on this occasion for joining us and delivering an exceptional keynote address on computational aspects of freeform machining. I'm sure the computational enthusiasts of mechanical engineering research fraternity has got a lot to learn from this session. And sir has also given you an opportunity to contact him So thank you, sir, for your kindness. And I'm sure the participants will find it as a great opportunity. Thank you, sir. Thank you, sir, for your kindness to join us, taking time from your busy schedule. I also thank you, sir. I also thank All India Council for Technical Education for sponsoring the conference, our publication partners Springer and American Institute of Physics Publishing for partnering with us on publication. I take the opportunity to thank Ms. Colinda and her team from Cadence for partnering with us and organizing the hands-on workshop on Omnis 5.1, a very efficient multi-physics software for computational analysis. And finally, I thank all our participants for being a part of the conference and for their very active participation throughout the event. Thank you all. And thank you, sir, once again. Thank you for joining us.
Thank you. Thanks for the opportunity given, madam. It is nice to interact with all the faculty members of SCMS and knowing you are head of the department and seeing Sanjeev back. I hope the conference has attracted a lot of interest among the researchers, and I'm sure that the conference proceedings will enlighten many of the researchers. Thank you.
Thank you, sir. Thank you.
Ladies and gentlemen, we come to the end of all the keynote sessions. I personally thank you all for your wonderful participation. Before we stand out, let me kindly remind you all to fill in the feedback through the link posted in the chat. Alone, we can do only so little. Together, we can do so much things. Yes, believing this tagline, ICCME 2021 takes you to the next panel discussion forum at 11:15 a.m. We have a very distinguished group of people gathering here for the discussion. We strongly believe the participants take this chance as an opportunity to interact with the experts. To guide the discussion and elicit the audience questions, I introduce Mr. Anup Kumar, Assistant Professor, SCMS School of Engineering and Technology, as the moderator. He will be soon joining you all. Please stay in the line. Thank you so much.
Good morning, all. Dear participants, this is Anup Kumar, Assistant Professor in the Department of Mechanical Engineering at SMA School of Engineering and Technology. So I'll be the moderator for the next event, which is the panel discussion. And we have the topic numerical techniques versus experiments in fluid flow and heat transfer. So our experts will be joining soon, and we will start the session at 11:15 a.m. Kindly stay with us. Thank you. Dear participants, we will begin this event shortly in 5 minutes. So speakers are joining. Kindly stay with us. Thank you. So dear participants, we are about to begin the session. So good morning to one and all present here. On behalf of ICCME 2021 and SEMS School of Engineering and Technology, I welcome all the participants to this great event where you can discuss your research problems with academic and industrial experts. As part of the AICT-sponsored Third International Conference on Computing in Mechanical Engineering, ICCME 21, we are organizing a panel discussion on numerical technique versus experiments in fluid flow and heat transfer. A platform where all of you will get an opportunity to listen to the views and experiences from experts of computation in mechanical engineering. The event will be conducted in 3 stages. Firstly, each speaker will be given 10 minutes each to produce their views and comments on the topic. After the first stage, the session will be open to the participants for the queries. At last, each speaker will be given 2 minutes to conclude with their statements. The session will be finally concluded by Dr. Rag RL, Head of the Department, Mechanical Engineering, SEMS School of Engineering and Technology. So I hope the speakers are well aware of the rules. I'll just repeat once more. First, each speaker will be given 10 minutes to produce their views and comments on the topic. Then we will have a session open to the participants for their queries. And finally, each speaker will be given 2 minutes to conclude with their statements. So next, let me take this opportunity to welcome our 6 eminent personalities who are the experts in the area of computation in mechanical engineering. So first of all, we have Dr. Ajit Krishnan R, currently working as a research associate in two-phase flow laboratory in School of Mechanical Engineering, Kookmin University, Seoul, South Korea. Dr. Ajit Krishnan was an overseas research fellow from India as a part of Korean Research Fellowship Program sponsored by National Research Foundation of South Korea. He completed his PhD from National Institute of Technology, Trichy in 2019. His doctoral research work was focused on the flow boiling in micro mini scale channels and their gravitational orientation effects. He has publications in reputed journals such as International Journal of Heat and Mass Transfer, Heat and Mass Transfer Springer, International Journal of Research Energy, etc. His research area mainly includes flow boiling in microscale channel, thermal management of electronics, dehydrogenation, microreactors, hydrogen generation and storage, steam methane reforming, etc. On behalf of SEMS School of Engineering and Technology, I welcome you, sir, to this panel discussion.
Thank you.
Okay, next we have the second expert, Dr. Rabi Roy KE. Dr. K. Rabi Roy is currently professor in Department of Mechanical Engineering, Dean International Collaborations and Head Career Guidance, and also Placement Unit of TKM College of Engineering, Kollam, Kerala. He has done his doctoral studies at IIT Madras, postgraduate studies at TKM College of Engineering, and undergraduate studies at College of Engineering, Trivandrum, Kerala. His research areas include computational fluid dynamics, finite element methods, bioengineering, and cryogenic materials. He is a doctoral research guide of University of Kerala and APJ Abdul Kalam Technological University. He is a permanent member of ICCME, member of Question Paper Preparation and Scrutiny Committee of Kerala Public Service Commission, doctoral committee member of Anna University, and research council member of TKMCE. He was instrumental in initiating 11 MOUs with various universities and industries around the globe for TKMCE. He was awarded funding from BK21 Plus Energy ODA Center by the South Korean government and the Department of Mechanical Engineering, Kookmin University, South Korea. He has more than 7 SCI indexed and numerous Scopus index publications in journals and conferences. He has also completed projects worth more than 30 lakhs funded by various agencies. So on behalf of ICCME School of Engineering and Technology, I also welcome you, sir, to this event. Next, we have Dr. Rahul Mishra, a postdoctoral fellow from IIT Bombay, Doctor of Philosophy in Thermal and Fluids Engineering, graduated in the year 2021 from Department of Mechanical Engineering, IIT Bombay, Maharashtra, India, and Department of Mechanical Aerospace Engineering, Monash University, Melbourne, Australia. He has done his Master of Technology in Fluid and Thermal Science in 2010 from the Department of Mechanical Engineering, IIT Kanpur, India. Dr. Rahul Mishra began his professional career as Project Research Assistant at Department of Mechanical Engineering, IIT Kanpur, and has served as Research Officer and later as Teaching Associate at School of Mathematics, Faculty of Science, Monash University, Melbourne, Australia. He has held the position of software engineer at various firms like Dassault Systems Solutions Lab and Siemens PLM Software Limited at Pune, India. With a keen interest in research areas of fluid structure interaction, mathematical methods for fluid dynamics, advanced heat transfer, computational fluid dynamics, finite element and boundary element methods, Dr. Rahul Mishra has published several papers in these areas. On behalf of ICCME School of Engineering and Technology, I also welcome you, sir, to this event.
Thank you.
Next, the fourth expert we have is Dr. Rajesh P. Nair, a PhD scholar in applied mechanics from IIT Chennai. Dr. Rajesh P. Nair started his professional venture as a lecturer in mechanical engineering at Jodhi Engineering College, Thrissur, Kerala. Dr. Rajesh is currently an assistant professor in chip technology, Cochin University of Science and Technology, Kerala. With an expertise in numerical simulation and finite element method, he has published several research papers in reputed journals and conferences and carried out consultancy assignments and research projects. On behalf of ICCME School of Engineering Technology, I welcome you, sir, to this event.
Thank you.
Next, we have Mr. Rakesh TV, Senior Research Engineer at Featherdyne Private Limited, Kalamassery, Kerala. A proficient in CFD solver development with good coding experience in C, C++, and Fortran, Mr. Rakesh TV is an engineering graduate in aeronautical engineering from the Aeronautical Society of India. He holds a master's degree from IIT Madras with an experience on coupled fluid flow, solute transport, and thermal transport simulation. Mr. Rakesh has 6 years of experience in working in the field of CFD as a project engineer at National Aerospace Laboratory and also in Fluidyne Private Limited, which is a commercial institution. Currently, as a senior research engineer at Featherdyne Private Limited, Kochi, Kerala, Mr. Rakesh is dedicated working on CFD simulations for optimizing drone designs. On behalf of ICCME School of Engineering and Technology, I welcome you, sir, to this event. And last but not the least, we have the sixth expert, Mr. Kunjuni Mohanan. Mr. Kunjuni Mohanan, an MTech graduate in thermal sciences from University of Kerala, started a professional venture as design engineer at Royal Extrusion Systems Private Limited, Pune, in the year 2016. Mr. Kunjuni later associated with Naval Physical and Oceanographic Laboratory, NPOL Kochi, as Junior Research Fellow in the year 2017. He's a former Senior Research Fellow from NPOL Kochi and currently is the Research Officer at SMA School of Engineering and Technology, Ernakulam, Kerala. During the tenure as a Research Fellow at DRDO, Mr. Kunjani has acquired experience in handling research intensive problems as well as time-bounded engineering projects which involve both fluid flow and structural analysis related to hydrodynamics. He also has keen interest in automation and optimization of repeating tasks with the help of programming. On behalf of SMA School of Engineering and Technology, I welcome you, sir, to this event.
Thank you.
So, without wasting much of time, we will begin the session. So, the session is a panel discussion on the numerical techniques versus experiments in fluid flow and heat transfer. So we have the first stage of the session where each speaker will be given 10 minutes. So first of all, I will call Dr. Ajit Krishnan R to this event. Sir.
Is it audible?
Yes, sir, it is audible.
Yeah, thank you, Anup sir.
Okay.
Have a great morning to all. Today it's one of the interesting panel discussion regarding this numerical techniques versus experiment, which all the research persons are going through after doing their experiment, how to do a numerical, and after doing a numerical, how to do an experimental. So it's a good discussion viewpoint as far as my observation. And first of all, I will thank SMS College for organizing such an event and inviting to give a talk regarding this. Basically, I'm working in the area of heat transfer and along with some hydrogen generation also. Actually, my problem is regarding this two-phase flow. That is means heat transfer along with a phase change. Usually, for example, we will take boiling or some sort of things. What my point of view regarding this numerical techniques and experimentation means, if we can able to predict this heat transfer in a simple domain or a simple system, it's pretty easy with a numerical modeling or by using some solver or some CFD. For my observation, for my problem, the issue is with there is a lot of phase change occurs. Some bubbles will develop. It will elongate to slug flow. Later, it will turn to some annular flow, some film thickness. A lot of flow patterns will arise during my heat transfer problems actually. Initially I feel it's pretty good to go through an experimental point of view to watch what were the things that happening inside a mini scale channel or some micro scale channel. Initially it will be nice to watch the things in a 1 mm or some conventional scale heat transfer. But when we go inside more to the micro scale heat transfer regions, it's pretty difficult to catch these physical phenomena. What was things that happening inside the channel? What was the heat transfer patterns? What was the flow patterns? I feel pretty difficulty in doing that experimental part when we are going much more detail into the micro scale heat transfer regimes. So the alternate choice is numerical, but it's also pretty difficult how to model all these domains because a lot of flow patterns are there. Some bubble will be there, some slug will be there, then it will elongate. So the issue is that we cannot able to combine all these in a single CFD model. So actually, in my point of view, what I am focusing is basically on the bridging the gap between these two. How we can bridge the gap between these numerical and experimental. So we cannot able to completely predict a problem. I mean, a complex problem by only simply a numerical simulation. Or sometimes this experimentation is very costly. We know that the sophisticated instruments and all. So I predict mainly to bridge the gap between these two, because some of the lacks of the experiments where we can't able to predict a particular thing, then we will go for a numerical thing and we will predict that, and we will fit the gap into the experimental, and then we can continue the research. So in my point of view, it's better to make a decision between a numerical and experimental. It's better to bridge a gap between these two. Then we can go smoothly with our result, because whatever the experimental can fail or it's cost to evaluate, we can evaluate by using numerical with a model, even though we can able to completely predict a particular problem with numerical only. So that's related to my experience in microscale heat transfer things. And I also worked on some micro reactors, that is mainly chemical reactors, that is mainly targeted in order to generate hydrogen. I think you all know about that steam methane reforming reactors. So in that case, an initial experimentation will be very, very difficult, because we don't know how a reactor behaves, where to place the burner, where to place that, how to keep a flue gas velocity at a minimum range, whether we need to keep it a maximum range, how the fluid will circulate inside, how the gas will develop, those things. So in that point of view, I completely depend on numerical simulation initially for my studies. Actually, the result that we have obtained from those chemical simulations of reactors and all, it's pretty really tally with that experimental result. We got a good close match when compared to that microscale heat transfer results. So basically, my point of view is towards it's the researcher choice to make a comparison between this numerical and experimental based on his research focus. It's first of all, we need to define the problem clearly, and we need to decide whether we need to go for a numerical, whether we need to go for an experiment. But for me, it's all work by bridging the gap between this numerical and this experimental. I'm not sticking to this one is good, this one is bad. I think both has their own limitations, mainly the cost for the experiment and all. So I'm mainly targeting on that, bridging that gap between this numerical and this experimental part, even though I'm an experimental researcher. And that's about my viewpoint regarding this.
Thank you, Dr. Ajit Krishnan. So that was really wonderful by sharing your views and comments on this topic.
Yes, sure. Thank you.
Thank you. So to continue with, we'll call the next expert. So we have the next expert, Mr. Kunjuni Mohanan, to give us views and comments on this topic. Over to you, sir.
Hello, thank you for inviting me. Can I please share the screen?
Sure.
But it is written here, was visible that attendee screen sharing.
So I'll just enable that.
Hi, am I audible?
Okay, sir. Yeah, it is audible and the screen is visible.
Okay.
You may
Thank
start.
you. So I worked at DRDO for 4 years, and I was working on this problem to estimate the pressure fluctuations on a flat plate when there is a fully turbulent flow over it. This is a very classical and one of the easiest problem you can do with numerical simulation. But the challenge I was assigned to was I have to make it viable for a workstation in an industry. Usually, this kind of academic work using large eddy simulation is done only in high performance machines in academic institutions as well as big industries. But to simulate to estimate pressure fluctuations over a plate using laboratory simulation was challenging on a small workstation. I have given a picture of turbulent structures over a flat plate. You can see the turbulent structures are very small due to the effect of viscosity, and it will be in a micro scale when you go near to the surface. So creating a huge domain and capturing all those instantaneous pressure fluctuations is a difficult task. So when it comes to experiment, when it comes to experiment and numerical simulation, for this particular problem, experiment can be considered an easy one because it can be done with a set of pressure sensors in a water tunnel. But for numerical simulation, the method with which can be done is very easy, but the mesh creation is a very difficult one. So my point in experiment versus numerical is that you cannot tell one is more advantageous than the other. Both of its merits and demerits, and sometimes we require both because solution in numerical solution without validation from experiment, I don't think how it holds much value in real world. And I forgot to mention this pressure fluctuation is a function of time and space. So the result I was able to get is a power spectra of pressure fluctuation in wave number and frequency domain. So in this specific case, what I understood is that the advantages in numerical method is that flow will not be disturbed by the sensor. But in the case of experiment, if we in some cases we cannot conform the shape of the sensor to the surface. Say if it is a flat surface, it may be okay. For a cylindrical surface, it may be difficult. So in that cases, the flow may interact with the sensor and the flow structure will be disturbed. In that cases, the experiment value will be, the result from experiment will not be that good. But in the case of numerical method, we doesn't have such restrictions. Next one is the high wave number measurements. High wave number measurements means how, if you place two sensors close by, the wave number means how, high wave number means how close we can space the sensors. It is limited by the sensor size in the case of experiments, but in case of numerical method, it is only limited by the mesh size. If we have a large computational resource, we can have high refined meshes. Thus, we can go up to how many wave number we require. Then, in numerical methods, measurements are not affected by external noises, such as there can be electrical noises, ambient noises, which can interfere with this pressure measurements. And the advantages with the experiment is that when we measure pressure fluctuations at low wave number, that means for a long distance, that is very easy with the experimental setup because we only need to place sensors very distance apart. But in the case of a numerical method, the disadvantage is that we have to create a long domain. Then our difficulty in solving that mesh in a small computer system will be very difficult. That will not be feasible. But that difficulty will not be in an experiment. And the other thing is that when we measure high frequency fluctuations in real world experiment, the high frequency fluctuations mean how quick we are measuring the pressure. That is only limited by the response time of the sensor, how fast the sensor can pick up the pressure fluctuations. And it doesn't affect how much time we are running the simulations for. But in the case of a simulation, the time step with which you are simulating the problem is the main factor that is affecting the high frequency measurement. And if you are reducing the time step to a very low value, that will affect the total duration of the simulation to be over. Some cases it can take months to complete a simulation. So that is a huge factor in making these kind of problems industrially viable. So to conclude, I will again repeat that this experiment and numerical method should go hand in hand, and only with the validation, this numerical results have any industrial value, and without experimental results, validation, we will get a result, but we cannot accurately judge whether it is correct or not. Here on the left side, what I have shown is an experimental result, and the right side, what I have shown is a numerical result. It may look similar, but we can only identify the errors and physics only if we compare it with the experiment. Okay. Thank you.
Thank you, sir. So, thank you for sharing your experience by putting an insight into your research project at the DRDO. So, Mr. Kunjini has enlightened us upon the advantages of both the numerical analysis as well as the experimentation. Thank you for the wonderful comments. So, next we'll have Dr. Rahul Mishra for the next few minutes. Sir?
Yeah. So, okay. So basically, this is the shared screen. Should I? Okay, fine. No issue, no issue. So basically, I have my experience as a researcher, as an industrial experience, as a early stage researcher when I was doing my MTech. So I have my experience. So when I was doing my MTech during the research experience or my early research experience. So during the projects in the coursework, we have seen that we are very fascinated by our CFD. So even though at the BTech level also, we are very fascinated by the CFD. Yeah, obviously CFD has grown steadily since its inception, and it has making it very attractive for a design and safety calculation. But as my previous speaker said, so before CFD can be used for a decision making, the uncertainty or the of calculation. So if you want to use some of the results, so how do you know that whatever results you obtain or whatever code or whatever simulation is correct or not? So obviously before CFD can be used for any decision making in calculation, it has to be estimated, it has to be verified. Okay, and to quantify the uncertainty, that is our code or our solution is working fine or not, so it must be validated by some experimental data. So here experimental data come into rescue. So we cannot fully rely on the CFD at which I observed during my MTech projects or during my early PhD coursework time. So we have developed the code, but we don't know whether our results are correct or not. So obviously we need some kind of validation. Also, when I was working in the industry, so before joining PhD, I worked 5 years for industry in Siemens PLM and CATIA Dassault system, as well as the CAD experience, CFD experience, and computer design experience, and the CAE experience. So based on that, I found that, so obviously CFD is used for initial design. Okay, we cannot rely on, suppose you want to manufacture some products, some automobile industry, so you need to manufacture them, but you cannot at the start you go on manufacturing things. Before that, you need some kind of calculation. So CFD is used for initial design stage, where many preliminary designs has to be evaluated for its performance. So once the couple of designs, 2 or 3 designs are shortlisted, then we do experiments. Okay, so at our level, when I was industry, we just give the designs. Okay, we are not in the manufacturing unit, but whenever it crosses to the next level for manufacturing stage, so we do that is at manufacturing stage, we do some experiments to those shortlisted design. Okay, so this way, a cost and the time involved to evaluate all the initial designs will be reduced. So here CFD comes the rescue. So before, at the initial level, we do all kind of performance study, and based on that, we do shortlist some one or two couple of designs, and then we give it to the other level where the manufacturing is taking place. And also we have also found that by using this technique, that before going to the manufacturing level, by using these techniques, design can be verified that this particular products is comply with our customers. So sometimes what happens at some stage of your manufacturing, your customer came and say, oh, I was not expecting design, I have proposed something else. So before going to the manufacturing level, we just make sure that now it's the final stage of design. So please look at our results, our performance chart, and then if that products is comply with the customer's specification, that is on early design cycle, then only we'll move to the head. And in this way, it will accelerate the product development process. So we can directly go to the manufacturing stage, because now everything design is finalized by the customers. So whatever happens at the manufacturing level, it will be taken care by the customer because he has verified the things. Okay. So that is one thing. And third is whenever I was doing the PhD, so at the PhD level, I have seen that since at the PhD level, we have to do something new. We have to something as which has never been done. So in that way, I have seen that as there are many problems or many phenomena which there's no mathematical expression present. Okay, so what happens? You can do numerical study or any computational study. If you have some numerical, if you have some mathematical equation available, if you have some PD available, so you have a PD, then all you can discretize, and then you can using different algorithm, you can solve the problem. But what happens when you're doing something new? So you may not have any mathematical expression, you may not have any mathematics or any differential equation behind it. So so what happens when many phenomena which does not have a definite mathematical formulation, and then we have to rely on the experimental method to understand the physics of the phenomenon. Okay, so even though we don't have any mathematics, but still we can do the experiment, and then we can using the end result, we can understand what's the physics, and then based on the experimental result, we can go on to find what are the mathematics behind it, what is the differential equation, and then we write a research paper, and at that stage your work is recognized. So that is my PhD experience. Also, I have seen that obviously in experiment there is a high initial cost. You have to set up the experiment. Suppose you're working in, as I was working in the fluid structure interaction problem, that is vortex into vibration and fluid structure interaction. There is a fluid, there is a structure. So whenever a fluid moves, due to the passive effect of force on the structure vibrates. So it's quite simple problem. If you're talking from 2D point of view, we can have a simulation. We have our in-house code. Even you can use an NSAs or any COMSOL. But what happens if you go for a high Reynolds number, or if you go for something 3D simulation? The cost is very effective. The simulation cost is very effective. Okay, so in that case, you waste a lot of your time. So if I run a 3D case, even though we have a server is ready, even there's issue with server also. So when I was in India, there was 10 or 15 days of queue for run a simulation. When I was in Australia, there was 2-3 days of queue to run our simulation. Okay, so that is one issue. But the other issue is, even though you have got your server, or if you have your own system, your computer, if you run a 3D simulation, so it takes around 2-3 months to run one case of particular Reynolds number. Okay, so on that case, it's very expensive from simulation point of view for working at the high Reynolds number or the 3D simulation. But whereas if you have set up already ready, the initial cost have been done. So some of your seniors of your in lab, the wind tunnel is already ready. The measurement system, everything exists there. So in that case, you just need to have put your setup and then do the experiments. So that is what I feel. What is the experiment is cheap in the sense in terms of the time and the cost. So experiment is cheap if your setup is ready and yours problems which is based on either high Reynolds number, or it's based on something a 3D simulation. So that way experiment is easy. So what I feel that it depends on at which level you are, at which problem you are working, so everything. So sometimes even during CFD, you have to be validated by experiment. Sometimes you feel that I have a CFD tool, I have the software ready, but you know that if you run some particular high real number case or particular 3D case, the simulation cost is very high. And if you have already some experiment setup is ready in your lab, then you can do the experiment there. So both way, I feel that one and one, depending on the problem, depending on the situation, depending on your current your lab facilities, you can go for the either experimental method or using the numerical method. So that is what my experience during my industrial experience, during my initial MTech work, during the initial researcher, and as during my PhD experience. So that's all from my side.
Thank you, sir. Thank you for those wonderful comments by sharing your experience, which you gained during your academic venture and while working on your research problems. Thank you, sir. So next, I would like to call upon Dr. Rajesh P. Nair for giving us comments and views on this topic. Rajesh, sir.
Yes, thank you. First of all, thank you SCMS College of Engineering for giving me an opportunity to present my views on experiment and numerical methods. First I thought was that I will, even though my research is in solid mechanics, I thought I will make an attempt in fluid mechanics and try to explain what is the difference in terms of experiment and numerical method. As Rahul sir mentioned, I feel in order to give more knowledge rather than information on experiment and numerical methods, I will explain a bit of mostly on the solid mechanics aspects. So coming to the experiment and numerical method, everybody consider numerical method as virtual experiment, which is now the new trend, which most of the researchers are following compared to the experiment method because of the cost. As earlier speakers have mentioned, experiment methods is considered as the benchmark for numerical method, because if you consider numerical method, especially like finite element method or CFD analysis, basically there is a saying that it's a garbage in, garbage out. If you give the wrong input, definitely your results also will be wrong. And also the other aspects of numerical method is that it's having a lot of errors which can happen in terms of the mesh convergence and not giving the right solution techniques, etc., which can actually make bring errors in the results. So if you consider my PhD work, I did my PhD from Applied Mechanics, IIT Madras. There I was in solid mechanics division. We have another division called the fluid mechanics division also, and then another division which is called biomechanics. So in solid mechanics, my area of research was impact analysis of a bullet hitting a target and studying how the fragmentation is taking place using numerical method. So I depend entirely on the MATLAB coding, and in the MATLAB coding, I actually did the program and did parametric study, and then I compared, as I have told you, numerical methods is basically are more error can happen more in numerical method compared to experiment method. So I validated it with an empirical method. Empirical method means people will do experiment method and they will do a curve fitting, and from that they will write the equation for that curve. And so I compared my numerical results with the empirical results available in literature. Now, if you consider the case of a bullet hitting a target, even though it's solid mechanics is having a little bit of aerodynamics also comes in the picture, like rotation of bullet, etc. If you consider how this project was generated, or how the seed of thought for making this project to originate for my guide was that once he went to DRDO, and there he actually found that in the lab, in defense lab, they are actually firing the bullet and just to obtain what should be the minimum thickness of the target in order to resist the complete penetration of the bullet. They are doing a lot of firing on the bullet. So repeated experiments they are doing. So which is a costly affair. So my professor asked me, Professor Lakshman Rao, he asked the defense people, scientists, why can't you do a numerical method? So they said, okay, sir, can you do it as a project? So that's how my kid got a project, and he is actually given that subdivided that work to different people, including me. So in numerical method, the advantage is that once we have our results matching with experiment method, the main advantage of numerical method is that parametric study is so easy. We can actually vary the speed of the bullet, the shape of the bullet, the shape of the target, then even material also we can vary if the properties or if the deformation patterns are same. So all these are possible only in numerical method. If you try to do it in experiment method, it's definitely very costly. And also, suppose if you want to model a blast or an impact or a shock analysis, etc. Usually, if you want to set up in an experiment method, you have to get a lot of permission from different organizations, defense organization, and government organizations, etc. So definitely, numerical methods. That's how numerical method becomes so popular compared to experiment method. But as the earlier people have mentioned, experiment methods are considered as the upper hand compared to numerical method. But even in experiment methods also, people used to do repeated experiments so that just to verify whether you are getting the correct answer, and also that will actually give more accurate. And sometimes in some of the journal papers, like in Indian International Journal of Impact Engineering, there they won't accept a paper if your work is entirely numerical method. They will only accept your paper if you have some experimental backup associated with it. So experimental methods is considered as the upper hand. But being a numerical fellow, I prefer that for the initial researchers, it's better to go with the numerical method because a lot of commercial packages are available. Like for CFD, we have Fluent, Orcaflex, etc. And for the finite element, we have Abacus, Ansys, all these things are there. So that's all for the time being. Thank you very much.
Thank you, sir. Thank you so much for adding on to the merits and demerits of both the methods which are being employed in computing mechanical engineering. Thank you, sir. So the session is next open to Mr. Rakesh TV. Sir, you may produce your views and comments on this topic.
Thank you, Anu. Am I audible?
Yes, sir. Yes, sir. You are.
Okay. Thank you very much for having me for this wonderful session of panel discussion on numerical technique versus experimental studies. Thank you, SCMHS, for giving me an opportunity to talk about this topic. So before moving to the topic, I will just give the brief experience of me in the field of this numerical techniques and experiments. In fact, as a research student and also working in some commercial institutions, to be honest, I have done only very less experimental work. Mostly my work was based on developing some numerical techniques and working on different softwares, CFD softwares for solving the equations. So first, after graduating my degree, I joined National Aerospace Laboratory as a project assistant. And I have got wonderful opportunities to interact with most of the scientists working there, most of them working in this numerical studies, and also experiments, of course, are going on along with that. But there, I came to know some facts from experiments that the experiment cost and the time which is taken for doing an experiment is very high, as the other panel members told about this topic. Because once if we do the experiment and once we got the results, and if we want to change some parameters or if we want to change some geometry, we need to redo the experiment again with the same setup, which is very much costly. So one thing we can do for solving this problem is once an experiment is done, we can reproduce the same experiment as a numerical model, and we can start working on the numerical model till we get a good validation with the experimental model. And after that, we can change the design or any other parameters on the numerical design, numerical model to get the results as we need. So this is one of the advantage of numerical method. And of course, experimental method, it has its own accuracy. So basically, if we talk about numerical versus experimental results, we are actually talking about the cost and time versus accuracy. So experimental methods give more accuracy than numerical methods. So basically, in experimental setup, we have lot of instruments and lot of things we will include for setting up the experimental atmosphere. And also to reproduce the actual ambient condition, we have to use more sensors in that. So which is very costly, and once one of the sensor or one of the equipment is damaged, it will be very difficult for reproducing the experiment again, and we need to move, we need to stay for a lot of time for getting it replaced and those things and all. But in numerical methods, we don't have that difficulty. But in case of accuracy, for example, if you are working on a geometry which is very complex, and also if you are working on a flow condition which is very turbulent, or there are a lot of source terms or a lot of irregularities or unpredictable behaviors is happening on flow condition, then talking about accuracy, the numerical method will be less accurate than the experimental results. So if we want to make the problem very much simpler, we have to go through some assumptions so that the numerical model is very well deviating from the actual conditions, flow conditions available. So this is one of the reason people will go for experimental studies to get the actual real conditions to be simulated. And also one more thing which currently I am working on, which is on the drone designs. We have a freedom to go on changing our design geometries and iterate on it to get a better performance of the aircraft which we are designing. If we are doing some experiments, we have to build the same material or build the same drone structure again and again to get the helpful results. So this we can do it easily on numerical method. So of course there are many advantages and disadvantages in the both cases, but choosing which method is appropriate for a person who is academic or industrial depends upon him. Whether he needs the accuracy or whether he needs the cost and time which has to be saved depends upon the person who uses numerical techniques and experimental methods. Thank you for that.
Thank you, sir, for your briefing. First of all, your briefing, your experience in research problems and your projects, and giving up your comments. Thank you, sir. And last but not the least, I would like to call Dr. Ravi Roy KE for his comments and views on this topic. Over to you, sir.
Good afternoon. Am I audible?
Yes, sir, you are.
Thank you. First of all, I thank the organizers for giving me an opportunity to present my views on the numerical techniques versus experiments in fluid flow and heat transfer. Of course, I have seen most of the panelists are experts in numerical techniques, but I would like to explain something else in a different perspective. Maybe similar to whatever people have mentioned, but as I am not only a researcher, I am a person who promotes research in my college. I have my own views regarding each and every aspect, which I'll be explaining in another 5 minutes. Now, as everybody knows, numerical techniques and experimentations are important for researchers, but I really think we have to know that the type of research on areas involving fluid flow and heat transfer also matters for the selection of the appropriate method, whether it is numerical or experimental. Experimental and numerical research really could be closely linked. When one conduct experiments, they could take data, and in order to understand such data, a search of mathematical formula is pursued, and in some cases, interpolation techniques also could be used. It is true that experimental research gives you a feeling of some kind of accomplishment, and eventually you will have a feeling that really you have physically done something good. But of course, there are some other factors also to be considered. Now, in recent years, the personal computer has become as ubiquitous as the television. Today's students are completely at ease using a computer for everything. Using the computer to solve engineering problems has become an easy concept for today's students. Concurrent with the rise of the personal computer and its unprecedented computing power is the proliferation of software tools available for solving engineering problems. Today, there are numerous commercial packages that an engineering technologist may see on the job. Preparing the student to use computer-based tools has become an important part of engineering curriculum. As some of the panel members suggested, there may be some problems associated with the numerical methods, maybe in terms of the accuracy, but I do not really feel that the numerical methods, whatever are incorporated using the softwares, are inferior to whatever we do in terms of experiments, because the way in which the equations and other things are monitored and solved are becoming more and more different and accurate as far as the latest softwares are concerned. And the courses on numerical methods with the correct focus can meet this need for today's student. Now, although a course in coding for numerical solutions is not likely to be a core course in engineering courses, exposure to solution of engineering applications using commercial CFD software is typically found in the engineering curriculum. Based on an informal survey of institution websites, a course in numerical methods is a common element in many engineering science programs, most often appearing in the mechanical discipline. It is often a graduate level topic, but numerical methods courses do appear in undergraduate curricula as well, which improves the perception of the student to these numerical courses. Now, coming back to the solution methods, usually the combined result obtained from numerical and experimental works provides a good output of research work, which makes it possible to get a good publication or patent. Both numerical research followed by experimental shall have perfect results, though it is highly dependent on the research arenas. From my experience in numerical research, I could find that it is now difficult to publish numerical results in reputed journals, in spite of the normal thinking that experimental works are more easy to get published since one feels that the results are new. And also, we have to think about reviewers who are all senior professors who are experts in mostly experimental applications, and most of them doesn't prefer these sort of numerical methods. And time is changing now. People from lower age group are becoming reviewers nowadays, and they are accepting more and more numerical publications. And definitely you should know that these numerical works will become attractive very shortly, since these sort of happenings are taking place very recently and in a faster pace. Now, when we compare the results between simulation and experiment, we may find sometimes huge differences between the results. Which kind of error should be looked into to justify the difference between these two results? In experimental studies, factors such as human and instrument error, the scale of construction and inaccurate specifications of materials, etc., can lead to errors in the results of analysis and testing. Numerical methods are affected by the physical model selected and the parameters belonging to it. For example, if you are using a turbulence model, some parameters, of course, can be modified. And normally you have only general recommendations for doing that. On the other hand, the used mesh is another source of variations in results. The combination of mesh, models, adaptation, and convergence process actually affects the simulation. The use of correct software also matters a lot, since there are many open access softwares available in the market, which the user may not be aware of its authenticity. That is the reason why it is so important to validate numerical results against good experimental or any other good analytical results. But as I mentioned before, these parameters, this sort of validations, everything may cease very shortly, because the accuracy which can be attained in these sort of commercial softwares is improving. And as another panelist mentioned, actually it is garbage in and garbage out. But actually, similar to whatever he has said, nowadays, if you put a garbage inside a software, definitely it is not going to give you a good result, or it is not going to show you any result. That is what is happening in the recent developments, whatever we observe. So that means that if you are putting any erroneous things inside, the system will try to understand what exactly is that. And if it is an error, then it is not going to show you any output. That means that things are changing fastly, and therefore we have to make sure that these sort of things are being accepted in our society also. Now, in spite of all these facts mentioned and discussed in all forums, as I mentioned before, the type of research also matters for the selection of the appropriate method. The research, whatever we do, can be independent, can be collaborative, it can be project-based, consultancy-based, etc. But we know that ultimately only successful outcomes will finally terminate in a good publication or patent. It should be noted that good research output is mandatory for institute accreditations and rankings. However, from my experience, I would like to mention some interesting facts which may be useful for your research. Although independent research is found to be safe and peaceful with no liabilities, outcome may be restricted due to the limited resources and facilities available with institutions like ours. Because everybody knows that funding is a major concern. State level institutions like ours normally will not get good funding from the departments, whatever provide funding. And therefore, since enough funding is not available, the experimental setups, normally whatever we make, may not be sophisticated. They may not be able to give out good results because there can be many errors creeping inside. And therefore, again, sorting to numerical methods will actually be a boon to most of us, because many softwares, whatever we purchase, has got licenses which is extending over a period of time. And therefore, we can do so many exercises continuously in these sort of softwares. And now, as my research activities are concerned, I have mentioned that I normally do some research, of course, at TKM College of Engineering, but I also promote other faculty members to do research, basically because we are very good in numerical capabilities. We promote numerical capabilities at our college, and we have developed collaborations with more than 36 universities throughout the globe. And actually in 2013, when we started our relations with University of Twente in Netherlands and Karlsruhe Institute of Technology in Germany, we never thought that these collaborations will really help us to gain a lot of attraction and advantage in the future. And in 2015, actually, we developed relations with Kumin University in South Korea, from where one panelist has appeared. And actually, we could do the numerical parts from TKM College of Engineering and the experimentations from the Kumin University, and we could combine these two and then send to good journals. And we have really achieved getting publications from good publications. And actually, that is only because we had a collaborative research work, which may be useful for other institutions also, which can combinedly do some work and then develop themselves. And whatever we have done at Kumin University is something like the needleless drug delivery system, which was actually carried out in the biomechanics lab in the university under Dr. Kim. And after understanding the capabilities, whatever we have at TKM, they have actually taken 5 of our students for PhD and more than 7 students for internship programs with total funding from Kumin University. Actually, we need not pay anything for that, for the PhD programs or the internship programs from our student side or the college side. Everything is funded by the university in Korea. And also, I actually got funding from the South Korean government for these sort of works. And also, I could visit this university 4 times in the past before Corona affected us. And maybe after the problems stop, I think I can go there again. And also, regarding another area, which is microchannel cooling, we have a collaboration with University of Technology in Malaysia. And again, combinedly, we could present a paper in a conference in Kaishu University in Japan. And again, we are trying for collaborations with them also. And again, basically, we have agreed for doing numerical works at our college, and then the experimentations will be carried out there. And of course, many of you will be knowing that the imprint projects, whatever are given by the government of India by DST, actually is meant for only IITs and IISc. But actually, we could get into that also in a project which is allotted to IIT Guwahati, which was actually related to the porous radiant burner. The entire CFD part is done by our college, and the experimentations were carried out there. And we had several rounds of discussions which resulted in good papers. And recently we have taken up another work, which is the sensorless assessment of temperature levels in fluids with a professor in Mahidol University, Thailand. And also we have another collaboration with the Southeast Missouri State University regarding the respiratory airflow analysis. And whatever I have mentioned right now are all personal works of mine, which involves tremendous amount of numerical analysis, which was done through the CFD software, particularly Fluent. And extending this, actually, many of our professors are doing collaborative works. Basically, the numerical part and the experimentations being done at the other university. I think something like 36 collaborations are right now going on, which actually helped us a lot in improving our perception and improving our rankings in MBA. So I think these sort of collaborative works will be useful for many of our universities where the funding is lacking. And I think you can make it as a model for improving the research in the colleges and therefore improving the rank and ratings as far as the government of India is concerned. Now, this is what I wanted to explain to you regarding my views on the research on the fluid flow and heat transfer analysis as far as numerical and experimentations are concerned. And in all, I think we should have to concentrate more on numerical methods for a better output and the survival of our institutions because of the restrictions, whatever we have in sort of funding and other problems. Thank you.
Thank you, sir, for giving us your experience and the facts related to our topic for the panel discussion. Thank you very much. Now, the session is open to participants. Before that, there is an overall conference feedback link, which will be posted in the chat box. All participants are requested to fill in the feedback link of the overall conference. Now, the session is open to the participants. Participants may ask your queries in regard to this topic on numerical techniques versus experiments in fluid flow and heat transfer. Participants may also post the questions in the chat box. Participants, any queries or any concerns related to this topic, you may ask to any of our experts. Participants can also put your questions in the chat box. Dear speakers, I think we do not have a question so far. We will give some more time to the participants. They may come up with the questions. So we will move on to the next stage of this session. So now the session is open to the experts or dear speakers for discussion. Any of the speakers, if you are having any questions or any queries or something to add on, you may ask or you may kindly put your comments to the others. So first of all, I would like to call Dr. Ajit Krishnan R. You may ask any queries to the other experts.
Hi, sir. Actually, it's a good discussion. I can also able to learn a lot. Actually, basically, I'm an experimental researcher, and for the past 1.5 years only, I'm touching with this numerical things. And also, previously, I am not knowing. I think Dr. Rabbi sir, because now only I got the clear picture, because we have a lot of connections from TKM. Now I got the clear picture why those connections in Kumin University. Okay, nice to meet you, sir. And basically, while discussing about these numerical and experimental concepts, the basic conclusion that what I drawn from this discussion is that both as their own merits and their demerits. Some persons, they may prefer numerical because they are sticking more to numerical. Some persons to experimental, as their studies was always experimental. But anyway, there is a validation part for any study. There is a validation part. Many times I have seen that some persons done numerical studies and they validate with experiments. Sometimes if we done some experimental work and submit to some journal, they will ask, where is the numerical validation? So I'm confused with this one. Why people are always keeping those experimental, they ask for numerical, they will ask for experiment. Actually, because I'm pretty confused with many revisions or many responses from these reviewers. Whether you validate your work, which side validation is actually a validate? Is this experimental or is it numerical? I'm pretty confused during my PhD studies regarding that part. Later on, I'm thinking about why we are sticking to a single element. Can we bridge the numerical and experimental? I think many panelists, including Rahul sir and Rajesh sir, told if we are not very much interested in experimental, or if we are not having facility to do that, start with an experimental, do with a model, or if you want to find some mathematical equations from that, find it, then proceed with the numerical. I think that will be a better way, which all persons can agree, because we have already done some experimental and we got a model which will work with that experimental. So we can do the parametric study over and over, whatever the model, whatever the size, velocity, temperature, whatever things we can vary by using numerical models, until the cost of that simulation is not going higher than the present experimental work. So I think that will be a better way. But I don't think so. We cannot completely avoid experiment. Why? Because it's a reality actually. It's a real-time simulation. I can say it like that. I like to say experimental work as it's a real-time simulation. What it's going to, if it's become a final product, how it is going to perform in a real-time environment. That means somewhat related to experimental. But I know it has a lot of drawbacks, including some panelists told that if you position a sensor inside a flow tube in order to measure the velocity, or in order to measure the temperature, there is a small boundary layer or some flow disturbances. It may create some eddies. Especially for my case, during microchannel, if I want to measure the inside temperature, if I insert a thermocouple in a 0.1 mm channel, entire experimental thing get collapsed. So I need to find some alternate way to measure those things, and that will be costly too. I know that will be costly too. So I think we cannot avoid completely, but we can bridge between numerical and experimental as far as my observation. And that's that's what I can suggest from these discussions.
Okay, thank you, Dr. Ajit Krishnan. That was so wonderful of you. I would ask the other speakers if they want to add anything to Dr. Ajit Krishnan's statements or comments. Okay.
Can I speak?
Yes, yes, Rakesh. Sir. You may.
So I truly agree with what Mr. Ajit told about bridging a gap between the numerical and experimental techniques. Both have its own significant importance because without experimental results, we cannot judge the actual situations, what is happening in the real-time scenario. And for the numerical, we need a easy method to get the solution faster. And in the case of industries and all, we need the product to be done at a faster rate. So we cannot going on doing experiments again and again for getting the product ready. But one thing what I can think of now is with the experiments, we can make some benchmark solutions or benchmark problems, which we can fix it for validation of numerical results. Once these benchmark problems are validated, then we can move on with some changes which we need to make in the designs or in the flow conditions to get more and more exposure to the scenarios. And this we can done more easily by using numerical simulation procedure. So that's what I need to say about this. Thank you.
Thank you, sir. Thank you so much for adding on those comments. So I would request the other members who want to add their comments to Dr. Ajit Krishnan's or Mr. Rakesh sir's.
Yeah, I just want to add one thing that what Ajit mentioned. Actually, Ajit has a doubt like which one is better, experimental method or numerical method, because he said that even if we try to publish a paper which has experimental results, they will ask where is the numerical result. And obviously, the other part is sure, like if you try to publish a numerical work, they will ask where is experimental or analytical results. Because if you consider any of the problems existing now, we can make it into three categories. One is analytical, another is experiment, and the third one is numerical method. Analytical methods, we can use it for only closed form solutions where there's simple method happening like a cantilever beam. But if the same cantilever beam having a circular hole inside, we don't know which equation will be correct. So we will go for numerical or experimental. One thing that I feel like what Ajit has mentioned is that numerical methods may require experiment or empirical results for validation, but experiment methods may not require numerical validation. But as people always expect that we should know the new advanced technology, they feel like parametric study is better in numerical method, and in order to make if the reviewer want us to do some of the parametric study, they will tell okay, do it with the numerical method rather than with an experiment method. And as now Rakesh sir has mentioned, like experiment methods we cannot avoid, but consider the case of a meteor hitting a satellite, or in the case of a twin tower accident, or in the case of an offshore platform which is being set on fire. We cannot actually do all these things using experiment method because it's an impossible thing. The only option for us is to do a numerical study and see how it varies. But still, whether the results are correct or not is a question which we can actually do some of the approximations, like we can change parameters and see which parameter is having more influence, etc. So everything we cannot do it using experiment, like a wave basin for analyzing a ship model. If you want to set up a wave basin for a ship model, it requires 1 crore rupees for setting up that experiment. Numerical methods, but if you want to purchase a software, definitely it's also costly, but not up to that of the experiment method. So we have to definitely depend upon literature results and see how we can correlate our results with the literature. That's all. Yeah. Thank you.
Thank you, sir. I think Ajit sir must have got clarity on that small confusion he was having on that question. And not only Ajit sir, I think most of the emerging scholars who are new to this field of
actually what sir told is correct. One time when we upload paper, actually we have a test cell for fluid flow simulations, some microchannel test cell. Initially, the reviewer asked for this empirical, if you Nusselt number correlation, if you tally with any Nusselt number correlation, it's already available in that one, because generally we will do like that. Then he asked for again, what is the numerical study? He want the heat conduction, how the heat is flowing to the channel. He want numerically, it is one dimensional. He want to prove. So sometimes these things can happen. It's unavoidable. Okay, fine.
Okay, thank you. I think I think most of the participants who are here, who are the emerging scholars, they must be having this confusion in their mind. And I thank the experts for answering that big question. So I would like the other panelists, the speakers, to give their concluding statements. So first of all, I would like to call Mr. Kunjini Mohanan to give us a concluding statement.
Hi. So my concluding statement is that I totally agree with other panel members on the necessity of both experiment as well as the numerical simulations. The one extra thing I would like to add is that the main problem with doing an experiment is the cost and time associated with it. And if we were able to, not in all cases, but if we were able to simulate such cases prior to the experiment, we can design an experiment with less cost and with less time consuming with the results from the simulation. So and to conclude, I would like to say that both experiment and simulation are required for most problems, or they should go hand in hand. Sorry, go together. Thank you.
Thank you, sir. Thank you so much. Next, I would like to call upon Dr. Rahul Mishra to provide us a concluding statement.
So as a conclusion, I can say most of the time in my PhD, I did a numerical work. I feel that CFD is not a replacement for any experiments. Okay, so you cannot replace experiment with the CFD. You can just use CFD as an add-on to understand the fluid. So you can use as a CFD tool for your if you are starting any experiment. So I feel that CFDs cannot be anyway avoid, or the experiment cannot be avoided at all and use the CFD. CFD has to be used, but just as add-on, not as a part, not as a replacement for experiment. Also, I would suggest that if you are doing some experiment, one should have experience of both, doing anything, research or any work. So you have experience of both experiment as well as the simulation. So suppose if you are an experimentalist, so I would suggest that try to use some software package so that you have some knowledge and experience of CFD. And suppose if you are doing some numerical work or CFD work and you don't have the experimental facility, I would suggest that collaborate with some institutes, maybe IITs, maybe some other foreign institutes, as my previous speaker said. So you collaborate with your some institutes or some research organization so that you can have gain experience in experiment as well. So as nowadays, as my Ajit is saying that the experimental guy want a numerical work, numerical guy want experimental work for a validation. So at a research point, you have experience of both. Maybe you are experimentalist, it's all right, you have a thorough knowledge experiment, but you have some knowledge of the CFD using some software package. You don't require any development of coding or something, you have some knowledge of experiment. Similarly, if you are a numerical guy, you collaborate with some people, you have some experience of how to do experiments, what are the setup required, what are the sensor required, and how do we do measurement. So for me, one should have a knowledge of both. Obviously, you should have expertise in one field, but you should not avoid the other field. So that's from my side.
Thank you, sir.
Thank you.
Thank you for putting on your final comments. And next, I would like to call upon Mr. Rakesh TV, if he has any comments to be made. Finally, you may.
Yeah, so what Rajesh sir told before, it was correct, that we cannot do the experiments of the real situations like meteor hitting and all these kind of big scale steps. But what I suggest was, what my view is clearly that experimental setup we can scale down, and we can get some approximate, or not approximate value, a scale down value, which we can extrapolate to the real time situations using numerical techniques. And also one more thing, in the case of turbulence models and all, we have a lot of coefficients and a lot of constants which we cannot find it out numerically. So for getting those coefficients and getting out that constants, we need empirical formulas and empirical methods for getting it out there. So basically, my view is both are important. Experimental and numerical study are important, but both have its own aspects of significance. One in the case of accuracy, and one in the case of cost and speedy requirement of solutions. So thank you. That's my view on that. Thank you very much.
Thank you, Rakesh sir. Next, I would like to call Dr. Rabi Roy KE to provide his final concluding statement. With you, sir.
Yes. Again, I would like to mention something based upon my experiences, my own experiences. Now, when I was doing my doctoral studies at IIT Madras way back in 2000, there were very few numerical works being carried out at IIT Madras. Most of the faculty members, most of the professors, they were doing works on experiments. And I think I was one among the very few who have completed or submitted a thesis with papers, publications in numerical works. Most of the other students who have joined with me or who are working, they were doing in experiments. But later, we could find that the trend was slowly changing. Later, in another 5-10 years, there were many students who started doing works numerically. And now if you see, every laboratory at IIT Madras in mechanical has got students who are working in numerical methods, either in the CFD or FEM or any sort of finite difference method or things like that. So the things are changing. That is what I have seen over the period of years. And as the panelists mentioned, when you send up a paper for review, normally, even though it is a experimental paper, they may ask you for the numerical agreements with the results, whatever they have obtained for the experiments. And that is a common fact right now, even though there is nothing to be mentioned with regard to numerical things. But things are changing like that only because of the views of the reviewer. The reviewers are slowly accepting the importance of numerical methods. That is what I am seeing in this period of time. And therefore, it is not that we have to think that experiments should be, the CFD should be always supported by the experiments. Because the accuracy levels of the results, whatever we obtain, they are improving over this period of time with the different softwares available in the market. And I could say that the three publications, whatever I have got recently, publications in FEM, Fanderman method, they are all numerical things. There is nothing with regard to experimentations. And we could prove that it is possible for a state level college like ours, or a normal college like ours, it is possible to publish papers or good publications in good journals with good impact factors without having anything referring to the experimentations. That is what we have proved right now. And maybe after some time, we will see that. That's what I feel. When the softwares become more user-friendly and more informative and more oriented in a way that the input, if it is bad, it is not going to give results. And if it is bad also, then possibly they may tell you what exactly is to be done. That sort of developments are going on. So possibly maybe in another 5-10 years, you will see that even without experiments, you'll be able to carry out numerical works properly. That is what I just want to convey to you. And therefore, I would like to urge the audience or the people who are watching this to do more in numerical methods so that you will be able to really publish papers easily, even if there is no experimental facilities in your colleges. And ultimately, what we need is we need a couple of good publications and good patents. And if we want to aim like that, rather than waiting for the experiment or the funding, whatever is normally not available, if you can focus on numerical works, definitely the improvements will come out faster, at a faster pace, and thereby you can change the scenario completely. That's what I want to mention right now. Thank you.
Thank you, sir. Also, I would like to thank you for exposing the research projects and the works which are carried at your institution. Thank you so much. Now, I would like to call upon Dr. Rajesh P. Nair to give us final concluding statement. Over to you, sir.
Yeah. Thank you. Actually, I just want to add like what Reddy sir has mentioned, nowadays during Corona, we all are forced to sit at home and we cannot do any experiments. But if you consider ANSYS or softwares like ANSYS or Abacus, they have actually given a free version of student version for 2000 nodes and all. So numerical methods, if you do numerical methods, basically we can understand the physics or the phenomenon we can understand. And but just as Reddy sir has mentioned, validation is also an important part. So that's why we call it as research. If you go to PhD, it's called as research, because exhaustive literature review will actually able to understand what is the current situation in the situation, what's the current condition in the situation. Basically, with that actually we can do little more work. We can do a little. First, we have to repeat what people have done in the literature with our numerical results. Then, if we do some parametric study, then people will definitely believe. Otherwise, there will be a question comes whether it's correct or not. Even the one who is doing also will feel like I don't know whether it's correct or not. Logically, I can say that I am getting the results, but in order to understand that, an explained backup is always good. But as Sir has mentioned, numerical method is having the advantage like the easiness of doing, and also to understand the situation. We should definitely go with the numerical results. But remember that experimental methods will give more knowledge and more hands-on feeling rather than numerical method. So if we get a chance to go to IITs or NITs or we can collaborate with some of the labs like DRD or ISRO labs, we can actually able to get understanding of the real life problems also, because they may have good experience setups. Overall, I just want to say that as most of the speakers are mentioned, we cannot avoid one area and work only on the other area, because both are more related. If you consider the case of a viscoelastic material, etc., if you want to model viscoelastic material using a numerical method, we actually should do some of the little bit of experiment and get some stress strain curve. Then that input value has to be given as the input value for the numerical method. So without doing the experiment on the viscoelastic material, we cannot do it on a numerical method. So like that, a little bit of collaboration is also there between the experiment and numerical method. So that's all I just want to add. Thank you.
Thank you, sir. Thank you, sir, for those wonderful statement. And finally, the conclusion statement from Dr. Ajit Krishnan. Sir, anything to add? You may, please.
Yeah, yeah, it's fine, sir. It's fine. Yeah.
Okay, sir.
I don't want to extend much more this. Yeah, that's fine. Yeah, it's fine.
Okay,
thank you.
fine. Anyway, we are coming to the end of our session. So I hope all the participants, which include the emerging research scholars and students, must have gained a wonderful experience and a valuable insights for your future endeavors from our 6 eminent personalities during this session. So I would open the session to the participants. If you are having any queries, you may ask to our experts. Participants, any queries? You may please ask to the experts. So since I think the participants are not having any queries, so I would like to call upon Dr. Rag R.L., Head of the Department, Mechanical Engineering, SMA School of Engineering and Technology, for concluding the session on panel discussion on topic numerical techniques versus experiments in the fluid flow and heat transfer. Over to you, Rag, sir.
Am I audible?
Yes, sir, you are.
Okay, thank you. Thank you. Okay, respected panel members and participants of the session. It was a fruitful session for comparing the computational and experimental research. All the panel members shared their expertise and experiences in a marvelous manner. From their views, we were able to understand several points. Let me conclude as wherever there are constraints like size, it is difficult to have experiments. But bringing all complexities to a real problem to a numerical model is also difficult. So bridging the gap by integrating both the methods is the best solution. As far as possible, validation using experiment is required even if we have a good numerical solution for the acceptance of results. Sometimes we cannot have experiments because the existing sensors or equipments may disturb the flow domain itself. There are several problems with no proper equations or partial differential equations. Such systems, we have to depend only on experiment. Time and cost-consuming numerical methods can be avoided and go for experimental setup, which is already available. Chances of errors are there in numerical methods. Experimental results have more accuracy and acceptance. Setting up an experiment is costly. Repeatedly, we cannot do experiments. So we can do experiments in numerical methods in a collaborative manner, and it is cost effective also. So better to do a benchmark problem and proceed to the numerical one. Nature of the problem is the basis of selection between numerical or experimental. The latest softwares for the numerical solutions are accurate and powerful since they are much refined. So such softwares can be used without any ambiguity. Validation using the experimental results in the literature can also be done. Finally, I will say merits and demerits will depend definitely on your working problem. Both methods are required to have a valid and acceptable result. Thank you all panelists for sharing your views and experience. Definitely, it will help the participants to take necessary decisions in their own research. Thank you all.
Thank you, sir. Thank you for concluding this session. So from this panel discussion, what we feel, I think most of the participants, they must have felt is that numerical techniques and the experiments are the two wings of a research problem. And a research, it won't fly until and unless these two wings, they function together. So I thank all our speakers and the participants who have accepted our invitation to this program and for being a part of this informative session. Thank you all. And this is T.M. Anup Kumar, Assistant Professor, the Department of Mechanical Engineering at ICCME School of Engineering and Technology. Thank you all. And over to you, Sanju sir.
Yes,
Thank
sir.
you.
Thank you. Thank you.
Thank you.
As all good things must come to an end, it's time for me to announce the end of the 3-day International Conference on Computing in Mechanical Engineering 2021. But before moving to any of our duties, we know no duty is more urgent than that of returning thanks. To serve the purpose, I invite Dr. Vidya Chandran, Organizing Chair, ICCME 2021, and Associate Professor, Department of Mechanical Engineering, SCMS School of Engineering and Technology. Over to you, Dr. Vidya Chandran.
Thank you, Sanju sir. Thank you so much. Now, let me fulfill my duty. Thanks to everyone. Distinguished panel members, Dr. Ajit Krishnan, Dr. Rabi Roy sir, Dr. Rajesh P. Nair sir, Dr. Rahul Mishra, Dr. Rakesh TV, and Mr. Kunyuni Mohanan, respected head of the department, Dr. Rag, other dignitaries, and dear participants. It is with great happiness that I step into the privilege of thanking this wonderful panel who has joined us online from various parts of the globe. I thank all the respected panel members for taking time out of their busy schedule to join us online and for making this session so lively and interactive. Thank you, Dr. Ajit, Dr. Rabi Roy sir, Dr. Rajesh sir, Dr. Rakesh TV, and Mr. Kunyuni for sharing your research experience with the participants of ICCME 21. Thank you.
Thank
Now,
you.
yes, thank you, sir. Thanks. Thank you. Thank you so much.
Thank you.
With this panel discussion, we are coming to the end of 3 days of knowledge sharing from experts from all over the world through keynote sessions, plenary sessions, and panel discussions. We, the Department of Mechanical Engineering, are happy and proud to have hosted the AICTE-sponsored 3rd International Conference on Computing in Mechanical Engineering, and believe that we have done justice to the theme of the conference and have benefited the research fraternity in the most suitable way. I thank our keynote speakers, Professor Dr. Geraldo Carbajal, Professor from Florida Polytechnic University, USA, Professor Dean Vucinic from the Brussels School of Governance, Belgium, Professor Dr. B.V. Reddy, Professor Ontario Tech University, Canada, Professor Dr. Alam Mohammad Mehboob from Harbin University, China, Professor Dr. Arul Prakash, Professor Department of Applied Mechanics, Indian Institute of Technology, Madras, and Dr. Shekhar M., Professor and Principal, AAA College of Engineering, Shivakashi, for being with us and delivering exceptional keynote sessions. I also thank All India Council of Technical Education for sponsoring the conference, our publication partners, Springer and American Institute of Physics Publishing. I take the opportunity to thank Ms. Colinda and her team from Cadence Numeka for partnering with us and organizing the hands-on conference workshop on Omnis 5.1, a very efficient multi-physics software for computational analysis. I thank all our reviewers and session chairs who have put in a lot of effort in providing directions to the authors and elevating the quality of the conference. Now, I thank our chief patron and chairman of SCMS School of Educational Institution, Dr. GPC Nair sir, for his guidance and support, and our patrons, Professor Pramod P. Thevanur, Vice Chairman, SCMS Group of Educational Institutions, Professor S. Gopakumar, Senior Senior Group Director, SEMS School of Engineering and Technology, and Dr. Praveen Sal, CJ, Principal, SEMS School of Engineering and Technology, for their motivation and continuous support throughout this event. On behalf of ICCME Organizing Committee, I thank Dr. Anida G. Pillai, Dean Academics, SEMS School of Engineering and Technology, for felicitating the conference and for all the guidance provided whenever we needed her help. I thank Dr. Rag, our head of the department and convener of ICCME, for leading us all the way and making this day happen. I also thank Dr. Venu and Dr. Shija, our former HODs, who initiated this conference and had proposed the conference to ICCME and guiding us all through. I thank Mr. Sanju AC, Assistant Professor, Department of Mechanical Engineering, for being the wonderful host of this conference, as always, and making the session flow freely, perfectly, and professionally. Thank you, Sanju, sir. And I thank the organizers of technical sessions, Mr. Sam Joshi, Associate Professor, and Mr. Surajar, Assistant Professor, Department of Mechanical Engineering, SEMS School of Engineering and Technology. I also thank Mr. Anup Kumar TM for organizing and hosting the panel discussion session so effectively. Now, I would like to thank my team, the Department of Mechanical Engineering, who are behind the screen, but whose efforts are visible from each and every session of this event. Thank you, dear colleagues, for your untiring efforts throughout 2021. Last but not least, I thank all the authors, co-authors, presenters, and participants of ICCME, who are the most important part of this conference. Thank you all for choosing ICCME, for sharing your research with the world. Once again, I thank our panel members for their valuable time and kindness in joining us. With this, I conclude, thanking Almighty for his blessings, with a hope to meet you all during the next edition of the International Conference on Computing in Mechanical Engineering very soon. Thank you.
Thank you, Dr. Vidya Chandran. Thank you all. We hope we will meet you again in future. ICCME 2021 and SEMS School of Engineering and Technology wishes you all a wonderful future. Thank you. Bye-bye.